What if I told you that the world you see around you, the solid ground beneath your feet, the vast expanse of the sky above, is only a fraction of what truly exists? For centuries, humanity has gazed up at the stars and wondered about the nature of our universe. But what if the answers we seek aren't just out there in the distant cosmos, but hidden in plain sight, woven into the very fabric of reality itself? This isn't science fiction. It's one of the most profound and thrilling quests in modern science, the search for hidden dimensions. Think about that for a moment. We're not just talking about distant galaxies or black holes, but dimensions, layers of existence that could be curled up, folded, or vibrating right alongside our own, invisible to our senses yet fundamental to the universe's deepest workings. It's an idea that stretches the imagination and challenges everything we thought we knew about space, time, and reality. This journey into the unknown isn't just for physicists in lab coats. It's a story about human curiosity itself, our relentless drive to peek behind the curtain of the observable and uncover truths that have eluded us for generations. From the brilliant minds who first dared to propose these radical ideas, to the cutting-edge experiments designed to detect the undetectable, this quest is as much about innovation as it is about inspiration. It asks us to reconsider what is possible, to dream bigger, and to embrace the wonder of not knowing, because sometimes the most revolutionary discoveries begin with a simple question: what if there's more? In this video, we're going to explore that question together. We'll venture into the world of theoretical physics, where mathematicians and scientists are using the power of imagination and rigor to map out realms beyond our perception. We'll look at how experiments with particle colliders and gravitational waves might soon provide the first clues, the faint whispers from these hidden dimensions, and what it would mean for us if they did. This isn't just about abstract concepts, it's about reshaping our understanding of existence, from the tiniest particles to the grandest scales of the cosmos. So, if you've ever looked up at the night sky and felt that tug of curiosity, that hunger to understand the mysteries of the universe, you're in the right place. Get ready to expand your mind and see reality in a whole new light as we journey beyond the observable into the fascinating realm of hidden dimensions. To truly grasp the audacity of this quest, we must rewind the clock and step into the intellectual whirlwind of the early 20th century. It was a time of profound upheaval in our understanding of the universe, a period where the very foundations of physics were being torn up and rewritten. Albert Einstein, with his monumental theories of relativity, had completely reshaped our conception of space and time, revealing that they were not separate, absolute entities but woven together into a single, dynamic fabric, the space-time continuum. Gravity, he proposed, was not some mysterious force pulling at a distance, but rather the warping and curving of this fabric by mass and energy. This was a revolutionary idea, but it also left a tantalizing puzzle. Einstein had described gravity beautifully within this geometric framework, but the other fundamental force known at the time, electromagnetism, stubbornly refused to be included in the picture. It was like having two different rule books for the same universe. This is where our story takes a fascinating turn with two lesser-known but immensely important figures, the mathematician Theodore Kaluza and the physicist Klein. In 1921, Kaluza had a breathtakingly bold idea. He asked a simple yet radical question: what if Einstein's four-dimensional spacetime wasn't the whole story? What if there was a fifth dimension, a tiny, unseen additional direction? By adding this one extra dimension to Einstein's equations of gravity, Kaluza found something miraculous. The equations not only still described gravity in our familiar four dimensions, but they also produced a perfect set of extra equations that described James Clerk Maxwell's theory of electromagnetism. It was as if by merely suggesting the existence of another dimension, gravity and light suddenly emerged from the same underlying geometric principle. This was the first serious scientific proposal for a unified theory of physics, and its key ingredient was a hidden dimension. Of course, an immediate and obvious question arose: if there's a fifth dimension, where is it? Why can't we see it or move through it? This is where Oscar Klein, a few years later, provided a crucial piece of the puzzle. He suggested that this fifth dimension wasn't like the vast, extended dimensions we experience. Instead, it must be curled up into an unimaginably tiny loop, a circle so small on the scale of the Planck length, a billionth of a trillionth of the size of an atom, that it is completely invisible to our senses and our instruments. Imagine a garden hose. From a great distance, it looks like a simple one-dimensional line. But if you could shrink yourself down to the size of an ant and crawl onto its surface, you would discover it has a second dimension curled around its circumference. Klein proposed that our entire universe might be like the surface of that hose, with our familiar four-dimensional reality existing on its breadth, while other dimensions are curled up so tightly we simply cannot perceive them. This Kaluza-Klein theory was a stunning intellectual achievement, a masterpiece of mathematical elegance. For a while, it generated enormous excitement. But as the new field of quantum mechanics began to explode, explaining the bizarre world of atoms and particles, the theory encountered problems. It couldn't successfully incorporate the strong and weak nuclear forces that were being discovered, and the scientific community's attention largely shifted away. The idea of hidden dimensions faded into the background, becoming a beautiful but seemingly forgotten footnote in the history of physics for several decades. Yet the seed had been planted. Kaluza and Klein had demonstrated that the geometry of higher dimensions wasn't just mathematical fantasy. It could have real, testable consequences for the forces that govern our universe. They provided the essential blueprint, the first scientific hint that reality might be far more spacious and richly textured than we could ever have dreamed, setting the stage for a dramatic comeback that would arrive half a century later. While the ideas of Kaluza and Klein were brilliant, they were, in a sense, ahead of their time, a beautiful but incomplete symphony waiting for its next movement. That movement began in the late 1960s and 70s, not with a focus on gravity or light, but with an attempt to solve an entirely different puzzle: the baffling behavior of the subatomic world. As physicists delved deeper into the nucleus of the atom, they found a zoo of particles and forces that defied easy explanation through the existing frameworks of quantum mechanics. It was from this chaotic and fertile ground that a new, radically different vision of reality began to grow, one that would not just revive the idea of hidden dimensions, but would explode it into an unimaginably vast cosmic landscape. This vision is known as string theory. The central, mind-bending premise of string theory is deceptively simple. For decades, we have thought of the fundamental building blocks of the universe, electrons, quarks, photons, as point-like particles, zero-dimensional dots with no internal structure. String theory proposes that this is an illusion. At the heart of every particle, if we could peer down to an almost incomprehensibly small scale called the Planck length, we would not find a dot. Instead, we would find a tiny, vibrating, oscillating loop of energy, a string. And just like a violin string can vibrate at different frequencies to produce distinct musical notes, a G, a B flat, a high C, these fundamental strings vibrate in different patterns. One specific vibration mode might give rise to an electron, another to a photon, another to a quark. In this elegant picture, the entire universe is a cosmic symphony. With every particle we see merely a different note on the vibrational spectrum of these tiny strings. But this beautiful idea comes with an extraordinary requirement, a mathematical truth that physicists discovered as they worked out the theory's equations. For the math to be consistent, for the theory to avoid nonsensical predictions like probabilities greater than 100% or faster than light travel, these strings cannot vibrate in just the 3 dimensions of space and 1 of time that we know. The equations only work if the universe has more dimensions. Early versions of string theory required a universe of 26 dimensions, but its most modern and promising incarnation, superstring theory, demands a reality with 10 dimensions. The latest variation, M theory, requires 11. We clearly only experience 4, so where are the others? This is where the genius of Kaluza-Klein made its triumphant return. The extra 6 or 7 dimensions string theory suggests are compactified. They are curled up into an exquisitely complex, tiny geometric shape at every single point in our familiar spacetime, a shape known as a calabi-yau manifold. To grasp this, try a simple analogy. Picture a single strand of a spider's web. To a tiny ant walking along it, the strand is a one-dimensional highway, a straight line to travel. But to our eyes, we see the strand is a 3-dimensional cylinder. Now, imagine if that ant was utterly incapable of perceiving that 3rd dimension. Its entire reality would be the line, completely unaware of the rich structure that contains it. String theory proposes we are those ants. Our 4-dimensional spacetime is the line we perceive, while the 6 additional dimensions are curled up into a complex, multi-faceted shape at a scale a trillion times smaller than an atom, a realm forever beyond our direct perception. The specific way these dimensions are folded and curled, the exact geometry of this hidden calabi-yau space, would determine the resonant frequencies of the strings, which means it would dictate the laws of physics themselves. The mass of an electron, the strength of gravity, the very constants of nature would all be a direct consequence of the geometric shape of these unseen dimensions. This is where the theory moves from being merely revolutionary to truly universe-altering. If the geometry of these hidden dimensions can vary, then perhaps our universe, with its specific set of physical laws perfectly tuned for stars, planets, and life, is just one possibility. There could be a vast, perhaps infinite, assortment of other universes, a multiverse each with its own unique calabi-yau geometry, and therefore its own completely different laws of physics. In most of them, atoms might never form, gravity might be repulsive, or the concept of a star might be impossible. We just happen to exist in one where the vibrational notes of the strings allow for our reality. String theory thus provides not just a potential theory of everything that unites gravity with quantum mechanics, but a profound explanation for why our universe is the way it is, transforming the question from what are the laws of physics to why do we live in a universe with these particular laws. While string theory gives us a profound new vision of reality's smallest scales, another equally radical idea has emerged to reshape our view of the largest scales of the cosmos. This is the concept of Brane worlds, a framework that suggests our entire universe might be just one surface, one membrane, adrift in a much larger and more expansive higher dimensional reality. The word brane itself is a shortening of membrane, but in this context it doesn't refer to a flimsy, biological layer. Instead, it describes a dynamic, multidimensional object, a universe in its own right, existing within a grander, bulk space of extra dimensions. In this startling picture, the 3 spatial dimensions we know and love might be all that is accessible to us because we, and every particle of matter and light we interact with, are fundamentally stuck to our particular brain, like characters living on the page of an infinitely vast book. This leads us directly to one of the most perplexing puzzles in all of physics, the shocking weakness of gravity. Think about it for a moment. A tiny fridge magnet can overcome the gravitational pull of the entire Earth, effortlessly leaping up to stick to the metal surface. Why is the force that holds planets, stars, and galaxies together so astonishingly feeble compared to the other fundamental forces like electromagnetism? Brane world models offer an elegant and mind-bending solution. What if gravity isn't weak at all? What if its strength is actually comparable to the other forces, but it is the only force that can freely leak or spread out into these extra dimensions of the bulk space? From our perspective, trapped on our three-dimensional brain, gravity appears diluted, its strength seeming to fade because its influence is spreading out into realms we cannot access. It's akin to being a two-dimensional being living on the surface of a pond. If a ripple spreads across the surface, you feel its full effect, but if a sound wave propagates through the air above the water, it would seem faint and mysterious, its true power dissipated into a dimension you cannot directly experience. This powerful idea was advanced and rigorously developed by theoretical physicists like Lisa Randall and Raman Sundram. In their models, our universe is a brain floating within a warped higher dimensional space, and this warping naturally explains why gravity is trapped near our brain at large scales, behaving as we observe it, while also allowing it to venture into the bulk at very small, subatomic scales. This isn't just a neat trick of mathematics. It has breathtaking implications for some of cosmology's biggest mysteries. For instance, what we perceive as the enigmatic phenomena of dark matter and dark energy, the invisible stuff that shapes galaxies and accelerates the expansion of the universe, might not be made of some exotic, unknown particles at all. Instead, they could be the gravitational influence of other, adjacent brains floating parallel to our own in the higher dimensional bulk. The gravity from stars and planets on a nearby brain could be tugging on our universe, manifesting as the extra, unseen mass we call dark matter. The push and pull between these cosmic membranes could even be the engine behind the accelerating expansion we attribute to dark energy. Perhaps the most spectacular implication of this brain world scenario is a new origin story for everything. The Big Bang, the colossal explosion that marked the beginning of our universe, might not have been a mysterious singularity emerging from nothing. It could have been the result of a cataclysmic collision between our brain and another one residing in the higher dimensional bulk. In this cyclic model, these membranes could periodically swing toward each other through the bulk, collide with unimaginable energy, creating what we see as the hot, dense Big Bang, and then bounce apart, setting the stage for the universe to expand, cool, and form galaxies, only to eventually be drawn together again for another collision billions of years in the future. In this view, the birth of our cosmos was not a unique, one-time event but potentially part of an eternal, rhythmic dance of multidimensional membranes. By visualizing our universe as a slice of a much grander multidimensional reality, the brain world concept forces a complete re-evaluation of our cosmic architecture. It provides a new set of tools to tackle problems ranging from the hierarchy of particle forces to the ultimate fate of space itself. This bold reimagining challenges us to think beyond the traditional boundaries of a single, isolated universe and invites us to ponder our place within a vast, multidimensional expanse, a cosmic ocean where other worlds, perhaps with entirely different laws of physics, might be floating just a whisper away in dimensions we have yet to directly observe. So if these extra dimensions are real, why can't we just reach out and touch them? Why don't we see doorways to other realms opening up around us? The answer lies in one of the most elegant and profound concepts in all of theoretical physics: compactification. Imagine the universe at its most fundamental level isn't a vast, empty void, but is instead buzzing with intricate, tiny structures folded into a space so small it defies imagination. This is the idea of the curled-up universe, a cosmos where the extra dimensions predicted by theories like Kaluza-Klein and string theory aren't absent. They are simply too small for our crude senses and instruments to perceive directly. They are compactified, coiled up into a scale known as the Planck length, which is about a billionth of a trillionth of the size of an atomic nucleus. At that scale, the familiar rules of our everyday world dissolve into the bizarre quantum realm. To visualize this, think of a common drinking straw. From a distance, it appears to be a simple one-dimensional line. But if you could shrink yourself down to the size of a microscopic ant and crawl onto its surface, you would discover an entirely new reality. The straw has a circular dimension curled around its circumference, a second direction of travel that was completely invisible from the macro view. Your journey is no longer just forward and backward. You could now travel in a loop around the straw's girth. Now take that concept and apply it to the fabric of spacetime itself. Theorists propose that at every single point in our familiar four-dimensional universe right here, right now, at the tip of your finger, there exists not just a point, but an entire six-dimensional geometric shape, curled up into a space 100 billion times smaller than that straw. Our entire reality might be the surface of an unimaginably complex, multidimensional shape, and we are like ants forever crawling along its length, utterly unaware of the rich, coiled geometry that defines the very laws of our existence. The specific form these curled-up dimensions take is not arbitrary, it is everything. In string theory, the vibrational patterns of the fundamental strings, the notes that determine whether a string is an electron, a quark, or a photon, are dictated by the exact geometry of this compactified space. The strings are so small that they don't just vibrate through our three spacious dimensions, they also wrap around and oscillate through these tiny, six-dimensional loops. The shape of these loops determines the possible resonant frequencies, much like the shape and size of a guitar's body determine the notes it can produce. A change in the geometry would change the allowed vibrations, which would in turn alter the masses of particles and the strengths of the fundamental forces. In this breathtaking view, the reason the electron has its specific mass and the force of gravity is so weak isn't a random accident of cosmic birth. It is a direct mathematical consequence of the hidden, multidimensional shape of the vacuum we live in. This is where the search for this true geometry becomes a monumental task for theoretical physicists, a quest to find the mathematical, lost chord of the universe. The leading candidates for these shapes are known as calabi-yau manifolds, named after the mathematicians who discovered them. These are not simple spheres or donuts. They are complex, multi-holed, fantastically intricate shapes with a specific mathematical property that allows for the supersymmetry required by superstring theory. There are potentially thousands upon thousands of different calabi-yau shapes, each one representing a different possible universe with a different set of physical laws. Our challenge is to determine which one, if any, corresponds to our reality. Scientists use powerful supercomputers to explore the properties of these shapes, calculating what the observable consequences would be for our universe if its hidden dimensions were curled up into a particular calabi-yau manifold. It is a process of reverse engineering the cosmos from the top down, using the laws of mathematics as our guide. But mathematics can only take us so far. We need experimental evidence. While we may never build a microscope powerful enough to directly see these Planck length dimensions, their influence might be detectable through subtle, indirect means. One tantalizing possibility is that they could manifest in powerful particle colliders like the Large Hadron Collider. If enough energy is concentrated in a collision, a particle might be kicked with such force that it briefly moves not just through our dimensions, but into a compactified one. From our perspective, this particle would seemingly vanish, violating the law of conservation of energy. The telltale signature of extra dimensions would be events where energy mysteriously disappears from our observable universe. Another clue could come from the cosmos itself. The specific way dimensions are compactified influences how the universe expanded after the Big Bang and could leave an imprint on the cosmic microwave background radiation, the faint afterglow of creation. It might even affect how gravitational waves ripple across the universe. Each of these potential signals is like a faint whisper from a hidden realm, a clue waiting to be deciphered by the next generation of experiments, guiding us closer to uncovering the full, magnificent architecture of everything that is. Of course, the most thrilling part of this entire quest is that it's not confined to blackboards and thought experiments anymore. We are actively hunting for these hidden dimensions, deploying some of the most sophisticated machines ever built to catch a glimpse of the unseen. This is where theoretical elegance meets hard, empirical evidence, and the primary tool in this search is the monumental Large Hadron Collider, the LHC. Buried deep beneath the border of France and Switzerland, this 17-mile ring accelerates protons to within a whisper of the speed of light and smashes them together, recreating the searing conditions of the early universe. Within the debris of these microscopic fireballs, physicists sift for clues, and one of the most tantalizing signatures they seek is something that seems like a magic trick: missing energy. The concept is brilliantly simple. We know from the unbreakable law of conservation of energy that energy cannot be created or destroyed. It can only change form. In a particle collision, we can meticulously account for all the energy before the impact and all the particles that come flying out afterwards. But what if some of that energy simply vanishes? In our three-dimensional view of the event, it would appear to disobey a fundamental law of physics. However, in a universe with extra dimensions, there's a perfect explanation. The energy isn't gone, it's just left our brain. A particle, or more specifically, a graviton, the hypothetical particle that carries the gravitational force, could be kicked so hard by the collision that it travels not just through our space, but into a compactified or bulk dimension. From our perspective, it's as if it disappeared into thin air. Finding an excess of these events where energy seems to vanish without a trace would be a powerful, indirect signal that something is carrying that energy into a realm we cannot see. But missing energy isn't the only ghost in the machine. Theorists predict other spectacular phenomena that could light up the LHC's detectors. Some models suggest that if extra dimensions are large enough, the collider could actually produce microscopic black holes. Now, before you envision a vacuum cleaner for planet Earth, these would be incredibly tiny, ephemeral objects. They would hawking radiate away their energy and evaporate in a fraction of a nanosecond, leaving behind a very specific and explosive burst of particles in their wake. While we haven't found them yet, their potential detection would be a monumental discovery, confirming not only extra dimensions but also our understanding of quantum gravity. Another signature to look for are Kaluza-Klein modes. Remember those particles theorized by Kaluza and Klein? They would be like heavier, excited twins of the standard particles we know, corresponding to the different vibrational modes as a particle moves through a compactified dimension. Finding a particle that looks exactly like an electron but with a much higher mass would be a direct echo from a higher dimensional reality. for those who prefer a quieter, more delicate approach than colossal particle smashers, another frontier of exploration exists on a tabletop. Some Brane world models propose that extra dimensions could be surprisingly large, as big as a fraction of a millimeter. While that might not sound impressive on the subatomic scale, it's enormous. At these tiny distances, the gravitational force should behave differently if it's able to spread out into these extra dimensions. Newton's law of universal gravitation, which says the force weakens with the square of the distance, might begin to weaken with the cube or a higher power of the distance at these microscopic scales. Experimental physicists are conducting exquisitely sensitive experiments using pendulums, torsion balances, and fabricated devices to measure the gravitational force between objects separated by mere microns. They are essentially trying to feel the shape of space itself with the most precise fingertips imaginable, searching for any deviation from the known laws that could indicate we are brushing up against the edge of another dimension. And the search extends beyond our planet into the cosmos itself. Ultra-high-energy cosmic rays, particles from deep space that strike our atmosphere with energies far beyond what any human-made collider can produce, could also hold clues. If extra dimensions exist, they might affect how these particles interact with the Earth's atmosphere, offering an astrophysical window into higher dimensional physics. Even the study of black holes and gravitational waves could provide hints. The way black holes merge and the specific ring-down of the gravitational waves they produce could carry an imprint, a subtle vibration, that betrays the existence of hidden dimensions warping the fabric of space-time around these monstrous objects. Every one of these experiments, from the colossal to the microscopic, represents a different path up the same mountain. They are all driven by the same profound curiosity to understand the true architecture of our reality. A positive result in any one of them would instantly transform one of the most speculative ideas in physics into a concrete feature of our universe, triggering a scientific revolution as profound as those brought by relativity or quantum mechanics. But even the absence of a discovery is a form of progress. It helps us refine our theories, close off dead ends, and sharpen our questions. This relentless, multifaceted pursuit is a testament to the very essence of science, a commitment to not just wonder about the universe, but to interrogate it, to test our wildest dreams against the unyielding standard of evidence, pushing our technology and our imagination to their absolute limits in the hope of catching a whisper from a world just beyond our sight. The echoes of the universe's most violent events might be carrying a secret message, one written not in light or sound, but in the very stretching and squeezing of space-time itself. The historic detection of gravitational waves didn't just confirm a century-old prediction of Einstein's. It handed scientists an entirely new sense with which to perceive the cosmos. These ripples, generated by colossal events like the mergers of black holes, travel across billions of light years, carrying with them an encoded record of their cataclysmic origins. But what if that record also contains faint, telltale signs of a reality beyond our own? This is the extraordinary hope now driving a frontier of research, using gravitational waves as the ultimate probe for hidden dimensions. According to Einstein's general relativity, a gravitational wave propagating through a pure four-dimensional universe, three of space, one of time, has a very specific character. It has two possible polarizations, often visualized as a plus shape and a cross shape, each stretching and compressing space in a distinct pattern as the wave passes through. But if our universe is embedded in a higher dimensional bulk, as Brane world models suggest, the story changes dramatically. The gravitational wave wouldn't be confined to our brain. As it travels, some of its energy could effectively leak into these extra dimensions. From our perspective, this would cause the wave to weaken or attenuate more than expected over large distances. It would be like hearing a sound from another room. The farther you are from the door, the fainter it becomes because the sound waves are spreading through the entire house, not just the room you're in. By meticulously comparing the observed strength of a gravitational wave signal with the predicted strength based on the event that created it, astronomers could find a discrepancy, an unexpected dimming that points to energy seeping into unseen realms. The polarization of these waves offers another powerful test. In a higher dimensional reality, the gravitational wave wouldn't just have two possible polarization states. It could have additional ones, often called breathing or longitudinal modes. These would manifest as a wave that doesn't just stretch space horizontally and vertically, but also radially, almost as if space-time itself is breathing in and out. Our current observatories like LIGO and Virgo are primarily designed to detect the two standard polarizations, but next-generation instruments, both on Earth and in space like the planned LISA mission, will be exquisitely sensitive to these subtler fingerprints. Finding any evidence of an extra polarization mode would be a direct and undeniable violation of pure four-dimensional general relativity, a monumental clue that the fabric of space-time is woven with more threads than we thought. Perhaps the most intriguing possibility involves the most extreme objects in the universe, black holes. When two black holes spiral inward and merge, they create a storm in space-time, sending out gravitational waves that ring down like a struck bell. The specific frequencies and decay rates of this ring-down are dictated by the properties of the final black hole, its mass and its spin. These are known as the quasi-normal modes, and they are a precise prediction of general relativity. However, if that final black hole is not just a four-dimensional object but is somehow connected to or influenced by extra dimensions, its quasi-normal modes would be different. The pitch and the decay of the ring-down would be ever so slightly altered. It's a minuscule effect, like trying to detect the subtle change in the sound of a bell if it were cast from a mysterious new alloy. But as our detectors become more sensitive and we collect more of these cosmic signals, we can compare the observed ring-down patterns against vast libraries of theoretical predictions. A consistent, unexplained deviation could be the signature of a black hole that isn't just a singularity in our universe, but an object whose true nature is tied to the geometry of a higher dimensional bulk. This transforms the most destructive events in the cosmos into the most precise laboratories. Each neutron star collision and every black hole merger becomes a natural experiment, testing the laws of physics under conditions we could never hope to recreate. The data streaming in from these observatories is not just about cataloging cosmic crashes. It is a continuous flow of information against which we can test our most profound ideas about reality. The convergence of gravitational wave astronomy with theoretical physics is a perfect example of how science progresses not in isolated silos, but through a beautiful dialogue between bold prediction and meticulous observation. As we refine our techniques and our detectors grow more advanced, we are essentially learning to listen more carefully to the symphony of space-time, tuning our ears to hear not just the loud notes, but the faint, hidden harmonies that might just be the key to everything. This profound connection between the invisible and the imperceptible brings us to one of the most compelling ideas in modern cosmology: the possibility that the mysterious substance known as dark matter isn't just made of some unknown particle in our universe, but could actually be ordinary matter from another dimension. Think about that for a moment. For decades, astronomers have known that galaxies rotate so fast they should fly apart, and that giant clusters of galaxies bend light with far more gravity than their visible stars and gas can provide. Something out there, something that doesn't emit, absorb, or reflect light, is exerting a tremendous gravitational pull, holding the cosmos together. We call this something dark matter, and it makes up about 27% of the entire universe. Yet, despite its overwhelming presence, every attempt to directly detect a dark matter particle here in our three-dimensional realm has come up empty. It's as if this stuff is fundamentally, almost intentionally, avoiding us. But what if it's not avoiding us? What if it's simply somewhere else? This is where the concept of hidden dimensions offers a breathtakingly elegant solution. In the Brane world scenarios we discussed, our entire universe is a three-dimensional membrane floating within a higher dimensional bulk space. Crucially, there's no reason to believe our brain is the only one. There could be countless other brains out there, each with their own stars, planets, and galaxies, each with their own laws of physics. Now, here's the key insight. The particles that make up all that matter on a nearby brain would be completely invisible to us. Light, the electromagnetic force, and the strong and weak nuclear forces are likely trapped on their own brains. They cannot cross the dimensional gap to reach us. But gravity, unique among the forces, can seep through the bulk. So, the gravitational pull from an entire galaxy made of normal atoms on a neighboring brain would be felt perfectly here in our universe. We would sense its irresistible tug, holding our galaxies together and bending the path of light. Yet we would see absolutely nothing to us. It would be the perfect description of dark matter. A ghostly, invisible mass that interacts with our world solely through gravity. This idea is refined further in specific theoretical frameworks with names like universal extra dimensions. In these models, the extra dimensions aren't just for gravity. Every known particle in our universe, like electrons and quarks, could have a heavy, shadowy partner, a kind of vibrational twin that exists because it can move through these additional spatial dimensions. The lightest of these partner particles could be stable, electrically neutral, and only interact with our world very weakly through gravity. It would be a perfect candidate for what we call a WIMP, a weakly interacting massive particle, which is a leading theoretical candidate for dark matter. In this view, dark matter isn't some exotic, alien substance. It's the hidden, higher dimensional counterpart to the very particles we are made of. It's a part of our cosmic family, so to speak, but one that lives in the rooms of the house we cannot yet enter. The implications of this are staggering. It means that our decades-long search for dark matter using massive underground detectors filled with liquid xenon or argon, designed to catch the rare bump of a dark matter particle, is actually a search for something far more profound. A successful detection wouldn't just tell us the identity of a new particle. It could be our first direct piece of evidence that our universe is part of a much larger, multidimensional reality. Even the absence of a signal in these experiments could be a crucial clue, pushing us toward models where dark matter is so secluded in another dimension that it only ever communicates with us via the faint whisper of gravity. Furthermore, space-based telescopes like the Fermi Gamma Ray Space Telescope scan the skies for indirect evidence of dark matter, looking for anomalous bursts of radiation that could be produced when dark matter particles annihilate. If that radiation has a specific signature that aligns with predictions from these higher dimensional models, it would be another powerful hint that we are seeing the shadow of another brain cast upon our own. This perspective fundamentally shifts how we view the cosmos. Dark matter is no longer just a missing puzzle piece in our own universe. It becomes a potential messenger, a cosmic pen pal from a dimension next door. It invites us to reconsider the very nature of reality and our place within it. The overwhelming majority of the universes mass the hidden scaffolding upon which every galaxy is built might not be missing at all. It might be residing right beside us, in a parallel universe separated by a dimensional gap thinner than we can possibly imagine, its presence only revealed by the gentle, persistent pull of gravity, a force that knows no dimensional bounds. Yet for all its elegance in explaining the weakness of gravity, this radical rethinking of our cosmic address leads us directly to one of the most persistent and puzzling issues in all of fundamental physics, a quandary so deep it's known simply as the hierarchy problem. At its heart, this problem is about a shocking imbalance of power. The four fundamental forces of nature are not created equal. The strong nuclear force that binds atomic nuclei together is 100 times stronger than electromagnetism, which is in turn 1,000 times stronger than the weak nuclear force. But then there's gravity. Gravity is almost unbelievably weaker than the others, a factor of 1,000,000 trillion times fainter than the strong force. To put that into perspective, the entire mass of the Earth is needed to hold a tiny fridge magnet to its surface against the electromagnetic force of the magnet itself. This isn't just a minor discrepancy, it's a gaping chasm in the very foundation of our physical laws, suggesting that our universe is built on a set of constants that seem almost arbitrarily and inexplicably fine-tuned. For decades, the prevailing assumption was that this problem would be solved at the immensely high energies of the Planck scale, the realm of quantum gravity, where the force should finally unite with the others in a grand symphony. But this scale is so far beyond our reach, energies a quadrillion times greater than what the Large Hadron Collider can produce, that it offered no practical path to an answer. It was a theoretical desert where calculations broke down. This is where the concept of hidden dimensions doesn't just offer an alternative, it completely reframes the entire problem. In the late 1990s, a trio of visionary physicists Nima Arkani-Hamed, Savas Dimopoulos, and Georgi D. Volley proposed a breathtakingly simple and powerful idea. What if gravity only appears weak to us because we're not seeing its full strength? What if its true power is diluted because it is spreading out into spatial dimensions that are, by subatomic standards, surprisingly large? Their model, often called the AD model after their initials, envisions a universe with extra dimensions that are not curled up at the Planck scale, but are instead much larger, perhaps as big as a fraction of a millimeter. In this scenario, our familiar three-dimensional universe is a brane, and gravity is the only force that can propagate freely through the higher dimensional bulk space. Imagine a powerful spotlight shining in a vast, dark field. If you are standing right next to it, the light is intense. But if that same light is now understood to be illuminating an entire enormous stadium, its intensity at your specific seat seems much dimmer because its energy is spread so thin across the entire space. In the same way, gravity's influence is spread across the full volume of these extra dimensions. We, trapped on our three-dimensional brane, only experience a tiny, diluted fraction of its true strength. The force isn't inherently weak, we're just only feeling a faint shadow of its full power. This elegant idea has a profound and testable consequence. If gravity's true strength is not set at the unreachable Planck scale, but is instead much higher because it's been spreading out, then the energy at which quantum gravity effects become important. The scale where the fabric of spacetime itself becomes grainy, and we might see the strings of string theory or create microscopic black holes, could be dramatically lower. Instead of being a quadrillion times beyond the reach of the LHC, this new quantum gravity scale could be just slightly above what our most powerful colliders can currently achieve. This means the hierarchy problem is no longer an abstract philosophical puzzle. It becomes an experimental one. We might not need a collider the size of a solar system to probe the secrets of quantum gravity. The next generation of particle accelerators, or even more sensitive analysis of data we already have, could potentially stumble upon the telltale signs, like those missing energy events or microscopic black holes, that would confirm we are indeed brushing up against the edge of another dimension. By allowing gravity to escape into a larger reality, the hierarchy problem transforms from a confusing flaw in our theories into a potential gateway to discovery. It illustrates how a multidimensional framework doesn't just add complexity to our models of the universe. It can actually simplify them, removing the need for the arbitrary and unsatisfying fine-tuning of constants that has long troubled physicists. The apparent weakness of gravity ceases to be a mysterious parameter written into the cosmos by hand, and instead emerges as a natural, almost inevitable consequence of the geometry of higher dimensional space. This shift in perspective turns one of physics' greatest embarrassments into its most exciting clue, a guiding light that directs our experiments and sharpens our questions, proving that sometimes the most profound answers come from daring to ask if our perspective on reality is simply too small. This incredible interplay between the very large and the very small brings us to one of cosmology's most successful yet mysterious theories: cosmic inflation. We've explored how extra dimensions might explain gravity's weakness and the nature of dark matter, but what if they also held the key to the universe's very first moment? The theory of inflation proposes that a fraction of a second after the Big Bang, the cosmos underwent a period of stupendously rapid exponential expansion, smoothing out the universe and planting the seeds for all future structure. It's a powerful idea that explains the observed uniformity of the cosmic microwave background, but it has always had a why problem. What was the nature of the inflattened field that drove this incredible expansion, and why did it start and stop when it did? The answer might not lie solely within our four-dimensional realm, but could be written in the geometry of a higher dimensional bulk. In the Brane world picture, our universe's greatest growth spurt could have been triggered by a dramatic event in the bulk. One compelling scenario suggests that the inflationary epoch was not sparked by a mysterious field within our universe, but was instead the aftermath of a collision between our brain and another. Think of it like two sheets of metal clanging together in a vast, silent warehouse. The tremendous energy released from that impact, reverberating across our brain, could have provided the exact kick needed to send space itself into a period of hyper-expansion. In this view, the Big Bang was not the very beginning but a phase transition, a cosmic reset button pressed by a multidimensional event. The inflation we theorize about would then be the calming down period, the settling of our universe after that colossal dimensional collision. Other models propose that the inflattened field itself, the engine of this expansion, is not confined to our brain. It could be a higher dimensional entity, a force that permeates the bulk. As this field evolved and its energy decayed in the bulk dimensions, it could have effectively rained energy down onto our brain, driving the rapid expansion we see from our limited perspective. The specific way this field rolls down its energy landscape, a process known as the slow roll mechanism, would be dictated by the geometry of the compactified dimensions. This means the precise rate and duration of inflation factors that determine the ultimate fate and structure of our entire cosmos were not random. They were a direct consequence of the hidden shape of the extra dimensions, linking the macro scale of galaxy clusters directly to the microscale of calabi-yau manifolds. This profound connection offers a potential solution to another long-standing puzzle: the astonishing uniformity of the universe. The cosmic microwave background shows that temperatures are the same in regions of space that, according to standard Big Bang cosmology, could never have been in contact with each other. This horizon problem is elegantly solved by inflation, which says these regions were once much closer together before being stretched apart. A multidimensional origin for inflation makes this even more elegant. If the triggering event was a Brane collision, it would have imparted energy uniformly across the entire surface of our brain simultaneously, ensuring a perfectly synchronized start to the expansion and explaining that uniformity in a very natural, geometric way. The most exciting aspect is that these ideas are testable. While we can't go back in time, the universe left us a fossil record, the cosmic microwave background. This faint afterglow of the Big Bang is imprinted with tiny variations in temperature and polarization, a snapshot of the universe when it was just 380,000 years old. The specific patterns in this snapshot are like fingerprints, and different models of inflation leave behind different fingerprints. If our inflation was driven by a Brane collision or a higher dimensional field, it could produce telltale signatures. For instance, it might generate a specific type of pattern in the gravitational waves that would have been produced during inflation, which in turn would leave a distinct curl-like pattern, known as B-modes, in the polarization of the cosmic microwave background. Experiments like the Simons Observatory and future space-based telescopes are actively searching for these precise imprints. Finding a signature that aligns with a higher dimensional model would be revolutionary, providing circumstantial evidence that our universe's genesis was a multidimensional event. This perspective beautifully weaves together the largest and smallest scales of physics. It suggests that the vast cosmic web of galaxies, the gentle whisper of the microwave background, and even the very laws of nature we observe today are all ultimately governed by the intricate, hidden geometry of dimensions we cannot see. The quest to understand inflation is no longer just about finding a field in our universe. It's about uncovering the dynamics of the bulk, a grander stage where our entire cosmos is but one actor. By peering back to the very first instance of time, we might finally catch a glimpse of the full, multidimensional architecture of reality, seeing how the universe's grandest design was shaped in dimensions beyond our own. But perhaps the most perplexing of all quantum phenomena is one that even Einstein famously dismissed as spooky action at a distance: quantum entanglement. This bizarre connection allows two particles to become so profoundly linked that measuring the state of one instantly determines the state of the other, regardless of the vastness of space separating them. This instantaneous correlation appears to violate the cosmic speed limit set by relativity, which states that no information can travel faster than light. For decades, this has stood as one of the greatest paradoxes in physics, a fundamental clash between our two most successful theories. But what if this apparent paradox isn't a flaw in our understanding, but a profound clue? What if entanglement isn't a mysterious, non-local connection through our familiar space, but a completely local connection through a dimension we cannot see? This is where the concept of hidden dimensions offers a breathtakingly elegant resolution. Imagine two characters drawn on a piece of paper, standing on opposite sides of the page. From their two-dimensional perspective, they are separated by a great distance, and any message sent between them would have to travel across the length of the page. But if the paper is rolled into a cylinder, a three-dimensional being could draw a line connecting the two characters by going the short way, directly through the air, a path that simply doesn't exist from the flatlander's point of view. In this same way, some theoretical models propose that entangled particles are not truly separated in the full, higher dimensional reality. They could be connected by a wormhole or a geometric bridge that tunnels through an extra compactified dimension, creating a shortcut that makes their communication instantaneous and local in the full bulk space, even though it appears impossibly fast and non-local from our limited three-dimensional vantage point. This idea, often referred to as ER equals EPR after a groundbreaking proposal connecting entanglement to Einstein-Rosen bridges, suggests that the fabric of spacetime itself might be woven together by these quantum connections. The spooky action isn't spooky at all, it's simply geometry. The strength of the entanglement between two particles could be directly related to the properties of this hidden geometric bridge. The wider and shorter the bridge in the higher dimensions, the stronger the entanglement appears to us. This provides a stunningly geometric basis for quantum weirdness, potentially weaving the two great pillars of physics, quantum mechanics and general relativity, into a single, coherent tapestry where information doesn't need to break any speed limits because it's taking a hidden dimensional shortcut. Researchers are actively exploring how to model this using the tools of string theory and the holographic principle, which suggests that our three-dimensional universe might be a projection of information stored on a two-dimensional surface at its boundary. In this view, entanglement is the fundamental currency that builds spacetime itself. The more quantumly entangled two regions of this lower dimensional boundary are, the more connected they are in the emergent higher dimensional space. It's a concept that turns reality inside out, suggesting that what we perceive as empty space is actually a complex and dynamic network of quantum connections, and that dimensions themselves might emerge from this quantum information. This is not just abstract theorizing, it has tangible consequences. The way black holes manage information, a puzzle known as the black hole information paradox, might be solved by understanding that the information isn't lost inside the hole, but is preserved in the intricate entanglement patterns between the hole and the radiation it emits. The quest to test these extraordinary ideas is pushing the boundaries of experimental physics. While we can't yet peer into extra dimensions directly, we can look for their subtle fingerprints in the behavior of entangled particles. Experiments that repeatedly test Bell's inequalities, the gold standard for proving the non-local nature of entanglement, are becoming increasingly precise. Scientists are looking for any minute deviation from the predictions of standard quantum mechanics that could hint at a deeper, geometric mechanism at work. Furthermore, the burgeoning field of quantum gravity seeks to find a unified description of nature, and any successful theory must be able to explain entanglement not as a magical exception, but as a natural feature of a geometric spacetime. By studying how entanglement behaves in extreme gravitational fields or near black holes, we might find the cracks in our current understanding that reveal the hidden architecture beneath. This fusion of quantum information science and dimensional theory is more than just an academic exercise. It opens a new window into the fundamental nature of reality. It invites us to reconsider one of physics' greatest mysteries not as an annoying paradox to be explained away, but as the most important clue we have. The strange, instantaneous connection between entangled particles might be our first direct glimpse into the true, multidimensional nature of the cosmos, a reality far richer and more interconnected than we ever dared to dream. It suggests that non-locality is not a bug in the universe's programming, but a feature, a profound signature that we are all part of a deeper, hidden dimensional whole. Yet for all the power of our most advanced machines and cosmic observations, there exists an even more fundamental tool in this quest, one that operates purely in the realm of thought and symbol the universal language of mathematics. It is through intricate equations and abstract geometries that these hidden dimensions first came to life, not as physical entities we could touch, but as elegant solutions on a page, waiting for reality to catch up. This is not a new story in physics. It is a tradition that stretches back centuries, where mathematical beauty has repeatedly served as a prophetic guide to physical truth. When Paul Dirac wrestled with the equation that bears his name, seeking to reconcile quantum mechanics with special relativity, his math insisted on something absurd: the existence of a particle identical to the electron but with opposite charge. That particle, the positron, was discovered just a few years later, the first known form of antimatter. Einstein's field equations, a masterpiece of tensorial calculus, predicted the existence of gravitational waves decades before we had any hope of detecting them. In both cases, the mathematics provided a map to a reality that our senses and instruments had not yet perceived. This same prophetic power is now being harnessed to explore the possibility of extra dimensions. The primary mathematical toolkit for this endeavor comes from fields like differential geometry and topology, which study the properties of shapes and spaces that remain unchanged even when they are stretched or bent. Think of a coffee mug and a donut. To a topologist, they are the same shape because one can be smoothly deformed into the other without tearing, as both have exactly one hole. This kind of thinking is essential when trying to envision how 6 or 7 spatial dimensions could be curled up into a space smaller than an atom. The specific shapes that satisfy the demanding requirements of string theory are known as calabi-yau manifolds, named after the mathematicians Eugenio Calabi and Xing-Tung Yau. These are not simple shapes like spheres or cubes. They are complex, multi-dimensional forms with intricate holes and tunnels, possessing a specific mathematical property that allows for the supersymmetry required by the theory. The power of these mathematical constructs is that they are not just abstract curiosities. They have direct physical consequences. The exact way a calabi-yau manifold is folded and curved determines the resonant frequencies at which the fundamental strings vibrate. One specific geometry might allow for vibrational patterns that produce the exact mass and charge of an electron, while a slightly different fold might change those properties entirely, potentially creating a universe where atoms could never form. By cataloging and studying the properties of thousands of these possible shapes, physicists can work backwards, using the known constants of our universe, the mass of the electron, the strength of the forces, to try and identify which calabi-yau manifold might describe our reality. It is a process of cosmic reverse engineering, using the language of mathematics to read the blueprints of creation. Another crucial field is group theory, which provides a formal language for describing symmetry. In physics, symmetries are not just about beauty, they are deeply tied to the conservation laws that govern the universe. The fact that the laws of physics are the here and now are the same as they were a moment ago is a symmetry that leads to the conservation of energy. Group theory helps physicists classify the possible types of symmetries that could exist in higher dimensional spaces, which in turn predicts the kinds of particles and forces that could emerge from them. This mathematical framework allows researchers to derive tangible, testable predictions from theories that would otherwise remain purely philosophical. For instance, the mathematics of certain higher dimensional models predicts the existence of Kaluza-Klein particles, heavier, excited twins of known particles, or specific patterns of missing energy that could be hunted for in particle colliders. Without this mathematical rigor, the search for extra dimensions would be a shot in the dark. With it, it becomes a guided expedition into the unknown. This profound partnership between mathematics and physics underscores a remarkable truth about our universe. It appears to be deeply, perhaps inexplicably, mathematical. The same abstract patterns and relationships discovered by mathematicians often find stunning application in describing the physical world decades or even centuries later. The non-Euclidean geometries formulated by Bernhard Riemann in the 19th century provided the perfect language for Einstein's curved spacetime in the 20th. This symbiotic relationship suggests that by exercising our creativity within the boundless landscapes of mathematics, we are not just inventing games of logic, we are perhaps tuning our minds to the fundamental frequency of reality itself, discovering the hidden structures that govern everything from the quantum realm to the cosmic horizon. In the quest for dimensions beyond our perception, mathematics is our most powerful sense, allowing us to perceive a reality that is otherwise utterly invisible, guiding us toward discoveries that will once again transform our understanding of the cosmos and our place within it. This journey into the possibility of hidden dimensions does more than just expand our map of the universe. It fundamentally challenges our very understanding of what is real. For centuries, philosophers have wrestled with the nature of reality, debating whether existence is limited to what we can directly observe and measure. The scientific proposal of extra dimensions brings this abstract debate crashing into the forefront of empirical inquiry, suggesting that the vast majority of the cosmos may be inherently, perhaps permanently, inaccessible to us, yet no less real for its invisibility. This is not a new idea in the history of thought. It powerfully echoes Plato's ancient allegory of the cave, where prisoners chained since birth mistake the shadows dancing on a wall for the entirety of reality, never comprehending the vibrant, three-dimensional world casting those shadows just outside their view. In this modern scientific context, we are the prisoners. Our familiar four-dimensional space-time might be merely the shadow play, a limited projection of a far richer, more complex multidimensional reality that we, bound by our biological senses, cannot directly access. This perspective forces a profound shift in how we define existence itself. If we accept that reality is not contingent upon our ability to perceive it, then the compactified dimensions of string theory or the expansive bulk of Brane world models must be considered as real as the chair you are sitting on, even if they forever remain beyond the reach of our most powerful instruments. This moves the discussion from pure metaphysics into the realm of scientific realism, where the best of our theories point toward entities and structures that, while unobservable, provide the most coherent explanation for the universe we do see. The strength of gravity, the masses of particles, the very laws of physics themselves, these observable phenomena become clues, the faint shadows on the wall that hint at the true shapes and structures hidden in the light of higher dimensions. Perhaps the most staggering philosophical implication is the potential for a multiverse. If the geometry of these hidden dimensions can vary, as string theory suggests with its landscape of possible calabi-yau manifolds, then our universe, with its specific, life-permitting constants, may be just one possibility in a vast, perhaps infinite, ensemble of universes. This directly addresses the long-standing puzzle of fine-tuning, the observation that the fundamental constants of nature appear perfectly calibrated to allow for stars, planets, and life. In a multiverse framework, this apparent fine-tuning loses its mysterious quality. We simply find ourselves in one of the universes where the dimensional geometry allows for our existence, while a nearly infinite number of other universes with different laws may be utterly barren. This transforms a potentially theological question into a statistical one, reshaping our understanding of our place in the cosmos from one of central importance to a humbling example of cosmic coincidence. These concepts inevitably brush against the deepest questions of consciousness and perception. If other dimensions exist, could they host forms of life, awareness, or existence that are completely beyond our comprehension? Our consciousness is inextricably tied to our biological brains, which have evolved to process information in a very specific three-dimensional environment with a linear flow of time. An entity that could perceive or move through additional spatial dimensions would experience reality in a way we cannot even visualize. Their thought processes, their very mode of being, would be as alien to us as our world is to a flatlander confined to two dimensions. This forces us to consider that what we call consciousness might not be the pinnacle of awareness, but merely one particular expression of it, limited and shaped by the dimensional constraints of our biological existence. Ultimately, the philosophical journey into hidden dimensions is a powerful exercise in intellectual humility. It reminds us that our current knowledge, for all its depth and sophistication, is likely just a glimpse of a much vaster, more complex, and possibly infinite reality. It shows how the age-old dialogue between science and philosophy is not just alive but thriving, as each discipline pushes the other to refine its questions and expand its vision. The quest to understand these unseen realms is more than a technical challenge. It is a fundamental part of the human drive to peek behind the curtain of the observable, to understand not just how the universe works, but what it truly is, in all its mysterious and multifaceted glory. Science fiction has always been a playground for the mind, a space where writers and filmmakers can unleash their creativity to explore the wildest possibilities of existence, and the concept of extra dimensions has been one of their most fertile grounds. From the Victorian-era time traveler who shifts into a fourth spatial dimension in H.G. Wells' classic novel, to the mind-bending tesseract used to communicate across time in the film Interstellar, these stories capture our imagination with the thrill of the unknown. They present dimensions as parallel worlds we can step into, realms where different histories unfold or where we might encounter versions of ourselves. This is a powerful and compelling narrative device, a canvas for exploring human drama against a backdrop of infinite possibility. It makes the abstract tangible and personal, allowing us to experience the wonder and terror of a multiverse from the safety of our seats. Yet, when we step from the movie theater into the world of theoretical physics, the reality of extra dimensions, as currently understood, is both more constrained and far more bizarre. Real scientific proposals are not about building a machine to visit a world where the dinosaurs weren't wiped out. Instead, they are grounded in a framework of mathematical rigor and a relentless demand for consistency with observable reality. In theories like string theory, the extra dimensions are not vast, open landscapes waiting to be explored. They are almost unfathomably tiny, curled up into a space billions of times smaller than an atom. You couldn't travel to them because there is no there to go to in the way we understand travel. Their existence is woven into the fundamental fabric of every point in our spacetime. They are a necessary part of the universe's architecture, not a destination. This isn't to say there's no overlap between the fanciful and the factual. The Brane world scenario, for instance, offers a speculative bridge between the two. The idea that our universe is a three-dimensional membrane floating in a higher dimensional bulk does indeed evoke the imagery of parallel worlds found in fiction. In this model, other branes could indeed exist mere millimeters away in an unseen dimension, potentially hosting their own stars, galaxies, and even life. The crucial difference, however, is the nature of interaction. In most science fiction, characters can see, touch, and communicate with these other worlds. In the Brane world hypothesis, we would likely be forever isolated. The forces that bind us, electromagnetism, the nuclear forces, are likely trapped on our own brain. We could only ever sense a neighboring universe through one fundamental, ghostly influence, gravity. Its pull might be the only whisper we ever receive from the cosmos next door. The relationship between science fiction and science fact is far from one-sided. While fiction often takes liberties with the science, it serves an invaluable purpose by inspiring generations of future scientists and fueling public fascination with complex ideas. The widespread popularity of string theory in the public consciousness can be directly traced to best-selling books and television documentaries that presented its dizzying concepts in an accessible way. This cultural moment didn't just make physicists into rock stars, it drew bright young minds into the field, eager to solve these magnificent puzzles. Fiction acts as a gateway, translating abstruse mathematics into relatable human stories and visual spectacles that make us yearn to understand more. However, this symbiotic relationship also comes with a responsibility to distinguish the scientifically plausible from the purely imaginative. Science is ultimately anchored by testable predictions and empirical evidence. A theoretical physicist's proposal for large extra dimensions is not considered valid because it's a cool idea for a story. It gains traction because it offers a potential solution to a concrete problem like the hierarchy of forces, and it makes specific, falsifiable predictions about what we should see in particle colliders. The scientific process is a harsh filter, discarding ideas that don't align with observation, no matter how elegant or narratively satisfying they may be. Science fiction, by contrast, is free to follow its own internal logic and emotional truth, prioritizing wonder and drama above all else. This beautiful tension between the two is what ultimately enriches our culture. Science fiction gives us the emotional and philosophical vocabulary to grapple with the implications of scientific discovery before it even happens. It allows us to ask, what if? In the most expansive way possible, real science, meanwhile, takes those questions and subjects them to the disciplined, collaborative, and often slow grind of experimentation and peer review. It tells us not just what could be, but what the evidence suggests actually is. Together, they form a feedback loop of inspiration and discovery. We can enjoy the thrilling tales of interdimensional travel while simultaneously marveling at the genuine, evidence-based strangeness of our universe, a place where hidden dimensions might dictate the laws of nature themselves, not from a distant realm, but from a tiny, curled-up geometry at the heart of every single point in space. Pushing the boundaries of human ingenuity to detect something we cannot see demands a level of technological ambition that rivals the theories themselves. While the Large Hadron Collider has been a magnificent tool in this search, the energy required to directly probe the Planck scale or create the telltale signatures of extra dimensions is staggering, far beyond its current capabilities. This is where the vision for the next generation of particle colliders comes into sharp focus. Imagine a machine not with a 17-mile circumference, but one spanning over 50 miles, a true titan of engineering known as the Future Circular Collider. Buried even deeper beneath the European landscape, this behemoth would accelerate particles to energies an order of magnitude greater than the LHC, essentially creating hotter, denser, and more energetic microscopic fireballs. Within the debris of these collisions, the probability of creating a microscopic black hole or kicking a graviton into a hidden dimension increases dramatically, transforming a rare statistical possibility into a tangible event we could actually hope to observe and study. But raw power alone is not enough. We need unparalleled precision. Detecting the faint whispers from other dimensions requires instruments of incredible sensitivity, capable of measuring the most minuscule distortions in space-time. This is the promise of a new era in gravitational wave astronomy. While ground-based observatories like LIGO and Virgo have opened this new window to the cosmos, they are limited by the seismic rumble of our planet and the finite length of their arms. The Laser Interferometer Space Antenna, or LISA, proposes to overcome these limitations by creating a gravitational wave observatory in the vacuum of space. Imagine 3 spacecraft flying in a perfect triangular formation millions of miles apart, connected by lasers of breathtaking stability. Free from terrestrial noise, LISA would be sensitive to a much broader spectrum of gravitational waves, including the low-frequency hum of supermassive black hole mergers. This sensitivity is key to detecting the subtle effects of extra dimensions, such as the anomalous attenuation of a signal or the presence of those extra polarization modes that would be a smoking gun for physics beyond Einstein's four-dimensional universe. On an even smaller scale, a parallel revolution is underway in the realm of quantum sensing. If some extra dimensions are surprisingly large, as some Brane world models suggest, their presence could cause Newton's law of gravity to break down at microscopic distances. Testing this requires measuring the gravitational attraction between two objects separated by mere microns, a phenomenally difficult task, as at such close range, gravity is utterly overwhelmed by other forces like electromagnetism. To overcome this, scientists are developing exquisitely sensitive devices using superconducting materials, cryogenic cooling to near absolute zero to eliminate thermal noise, and sophisticated vibration isolation. These tabletop experiments are like using the most delicate fingertips imaginable to feel the very texture of space itself, searching for any deviation from the inverse square law that would suggest gravity is spreading out into an unseen dimension. It's a humble, quiet approach compared to colossal colliders, but its potential to uncover a major discovery is equally profound. None of this, however, would be possible without a corresponding leap in our computational capabilities. The mathematics behind higher dimensional geometries, particularly the intricate calabi-yau manifolds of string theory, is fiendishly complex. Simply understanding the properties of a single proposed shape requires immense processing power. Researchers use powerful supercomputers to simulate how strings would vibrate within these hidden dimensional landscapes, calculating what the resulting particle masses and force strengths would be in the corresponding four-dimensional universe. The goal is to create a vast catalog of theoretical predictions, a library of possible universes, so that if a new particle is discovered or an anomaly is measured, we can cross-reference it against these simulations to see if it matches the fingerprint of a specific higher dimensional geometry. This fusion of theoretical mathematics with brute force computation is essential for turning abstract theory into testable science. Ultimately, this grand technological pursuit is a deeply collaborative human endeavor. It's embodied by international partnerships like the global consortium behind CERN or the multi-agency effort to launch LISA. These projects represent a shared global investment in fundamental knowledge, uniting thousands of scientists, engineers, and technicians across continents. The technological spin-offs from this relentless drive are themselves a form of discovery, catalyzing advancements in superconductivity, data processing, cryogenics, and materials science that ripple out into the wider world. The quest to find hidden dimensions, therefore, is about much more than answering a profound scientific question. It is a catalyst for our species, pushing the limits of our technology, our cooperation, and our imagination, demonstrating that the journey to understand the universe is also a journey that continually reshapes and elevates our own capabilities. While the vision of hidden dimensions is undeniably elegant and compelling, it's crucial to step back and acknowledge that this quest is not a settled matter but a vibrant and at times contentious scientific debate. The primary framework for these ideas, string theory, has been the subject of intense scrutiny and criticism, not because its goals are unworthy, but because the path it has taken presents profound challenges. The most significant of these is the stark lack of any direct empirical evidence. Despite decades of development and its breathtaking mathematical beauty, string theory has yet to make a single prediction that has been confirmed by experiment. All of its potential signatures, from supersymmetric particles to microscopic black holes, remain firmly in the realm of the theoretical. For many scientists, this is a fundamental problem. A theory that is so flexible it can accommodate almost any observational outcome without being definitively proven or disproven begins to stray from the testable bedrock of the scientific method. This issue is magnified by what is known as the landscape problem. The mathematics of string theory doesn't point to one unique universe with our specific laws of physics. Instead, it suggests the existence of a colossal landscape of possible solutions, perhaps 10 to the 500 or more different vacuum states, each corresponding to a universe with a different set of physical constants, forces, and particles. In this vast multiverse, our cosmos, with its conditions just right for life, would be a single statistical possibility among a near infinity of barren alternatives. For some, this offers an elegant explanation for fine-tuning. For critics, however, it is a capitulation. If the theory can predict every possible outcome, then it effectively predicts nothing at all about our specific universe. It risks becoming an untestable meta-theory about the possibility of all universes, rather than a precise description of our own. These challenges have spurred the development of compelling alternative approaches to the same ultimate goal, unifying general relativity with quantum mechanics. One of the most prominent is loop quantum gravity. Unlike string theory, LQG does not propose extra dimensions or fundamental strings. Instead, it suggests that space itself is not smooth and continuous, as Einstein described, but is rather woven from a fabric of tiny, discrete, finite loops, a network of intersecting threads of spacetime. In this view, the famous singularity at the heart of a black hole isn't a point of infinite density. It's a gateway to a region of extreme, yet finite, curvature that could potentially connect to another part of the universe or another universe entirely. LQG's appeal lies in its direct quantization of spacetime itself, offering a clear picture of a granular universe without relying on unobserved dimensions, and it makes specific, testable predictions about the quantized nature of space that might be observed in the light from distant gamma-ray bursts. Another fascinating alternative is causal dynamical triangulation. This approach is less about elegant equations and more about brute force computation. Imagine building a model of spacetime out of the simplest possible geometric building blocks, tiny, triangular pyramids called simplices. The rules are simple. Each block must connect to its neighbors in a way that preserves cause and effect. The future must always follow the past. By letting a supercomputer randomly assemble trillions of these blocks and observing what large-scale structure emerges from the chaos, physicists have made a remarkable discovery. This simple, bottom-up process doesn't produce a random jumble. It spontaneously generates a universe that has 4 dimensions, 3 of space and 1 of time, exactly like the one we inhabit. CDT provides a powerful argument that the 4-dimensional nature of our reality might not be a fundamental given, but an emergent property arising from more basic quantum rules, all without the need for extra dimensions. This diversity of thought is not a weakness of theoretical physics, it is its greatest strength. The vigorous debate between proponents of string theory, loop quantum gravity, causal dynamical triangulation, and other ideas ensures that no single paradigm becomes dogma. This healthy skepticism forces each camp to sharpen its arguments, address its weaknesses, and strive for that crucial, testable prediction that could elevate it from a beautiful idea to a confirmed description of reality. It reminds us that the path to unification is not a straight line but a wide-ranging exploration of many possible paths, each with its own insights and blind alleys. By examining these criticisms and alternatives, we gain a more balanced and humble perspective on the quest for hidden dimensions, appreciating that the final theory of quantum gravity, if it exists, may look very different from anything we have yet imagined, and its discovery will be a triumph not for one group of theorists, but for the collective, self-correcting enterprise of science itself. Translating these mind-bending concepts from the abstract language of mathematics into something the public can grasp and marvel at is a monumental task in itself, one that requires a special kind of creativity and passion. How do you explain a six-dimensional calabi-yau manifold to someone without a PhD in theoretical physics? The answer lies in the power of the analogy, a tool that has become indispensable for scientists and educators. Think of the classic example of a garden hose. From a distance, it looks like a simple one-dimensional line. But if an ant were to crawl onto its surface, it would discover a second dimension curled around the hose's circumference. This simple, vivid image, first used by Oscar-Klein, provides a tangible gateway into the idea of compactified dimensions, allowing anyone to grasp how something could be real yet hidden from our everyday perception. These analogies are more than just teaching tricks. They are essential bridges, turning impenetrable equations into relatable stories that spark a sense of wonder. This crucial work of demystification happens on many fronts, from the grand halls of science museums to the intimate screens of our personal devices. Institutions like the American Museum of Natural History create breathtaking immersive exhibits, using projection mapping and interactive displays to let visitors visually walk through a simplified representation of higher dimensional space. Documentaries and YouTube channels harness the power of computer-generated animation to bring these ideas to life, visualizing how gravity might leak into a bulk dimension or how strings vibrate to create particles. These platforms don't just present facts, they craft narratives. They tell the story of the quest itself, the decades of dead ends, the thrilling breakthroughs, the collaborative nature of the scientific process. By showing that science is a dynamic, self-correcting human endeavor rather than a static set of answers, they help audiences understand that not knowing is not a failure, but the very engine of discovery. Central to this outreach are the charismatic explainers who have become household names, figures like Brian Greene and Neil deGrasse Tyson. Through best-selling books like The Elegant Universe and captivating television series like Cosmos, they have performed a kind of intellectual alchemy, transforming the densest subjects into a source of public fascination. Their genius lies in their ability to convey the profound significance of these ideas without sacrificing their complexity. They never talk down to their audience. Instead, they invite viewers up to their level, using eloquent storytelling and carefully crafted metaphors to make the unfamiliar feel intuitive. A public lecture by such a figure is less a class and more a performance, leaving the audience not with the feeling that they have memorized a fact, but that they have been let in on one of the universe's most profound secrets. This inspiration is a critical catalyst, often serving as the initial spark that ignites a lifelong passion for science in a young student. The ultimate goal of all this effort extends far beyond simple explanation. It is about building and sustaining a foundation of public support for the basic research that makes these discoveries possible. The Large Hadron Collider, gravitational wave observatories, and deep space telescopes are funded by public money, and they require a societal consensus that values curiosity-driven exploration. By fostering a basic understanding and appreciation for this work, educators and communicators help create a world where citizens and policymakers see the value in investing in questions that may not have immediate practical applications, but which fundamentally expand the horizons of human knowledge. This engagement ensures that the quest to understand hidden dimensions isn't locked away in an ivory tower, but is recognized as a shared human adventure, a collective effort to understand our place in the cosmos. Perhaps the most beautiful outcome of this educational outreach is its power to democratize wonder. You don't need a particle accelerator in your backyard to ponder the nature of reality. Through the thoughtful work of communicators, the profound beauty of a higher dimensional universe becomes accessible to everyone: the artist, the mechanic, the student, and the retiree. It empowers people to look up at the night sky and not just see points of light, but to sense the incredible, hidden architecture that might underpin it all. This effort successfully bridges the immense gap between esoteric mathematical theory and the public imagination, ensuring that the thrill of discovery and the awe of the unknown remain a vital part of our culture, enriching our shared journey as we strive to uncover the deepest truths of existence. What truly makes this quest so remarkable is how it transcends the boundaries of any single field of study, weaving together threads from across the entire tapestry of human knowledge into a single, collaborative effort. This isn't just a project for theoretical physicists lost in their equations. It is a symphony of disciplines, each playing a crucial part in the search for a deeper reality. At the foundation, we have mathematics, the universal language of the cosmos. Pure mathematicians, often working without any immediate thought of practical application, develop the intricate frameworks for describing these higher dimensional spaces. They explore the properties of complex shapes like calabi-yau manifolds, providing the essential vocabulary and grammar that physicists then use to write the laws of a potential multidimensional universe. Without this advanced mathematical toolkit, concepts like curled-up dimensions or Brane worlds would be little more than philosophical musings, lacking the rigorous structure needed to make real predictions. But a beautiful equation alone is not enough. This is where experimental physics takes the stage, tasked with the Herculean job of asking the universe whether these elegant ideas are actually true. These are the engineers of reality, the ones who design and operate monumental machines like the Large Hadron Collider, who orchestrate exquisitely sensitive tabletop gravity experiments, and who analyze the torrents of data they produce. They translate abstract mathematical possibilities into concrete, testable signatures, a specific pattern of missing energy in a detector, a minute deviation in the strength of gravity at a microscopic distance, or an anomalous particle decay. Their work provides the crucial anchor, tethering our soaring theoretical imaginations to the hard rock of observational evidence, and ensuring that the quest for hidden dimensions remains a scientific endeavor, not just a flight of fancy. Looking outward to the grandest scales, astronomy and cosmology provide a different kind of laboratory. By observing the aftermath of the Big Bang in the cosmic microwave background, by mapping the large-scale structure of the universe, and by studying the gravitational waves from colliding black holes, astronomers gather forensic evidence from the cosmos's most violent and ancient events. They look for imprints that could only have been left by higher dimensional physics, perhaps a specific pattern in the primordial light, or an unexpected way that gravitational waves lose energy as they travel across billions of light years. The universe itself becomes the ultimate particle accelerator, and telescopes are our microscopes, allowing us to probe energies and conditions that we could never hope to recreate on Earth. And none of this would be possible without the silent, powerful contribution of computational science. The mathematics behind these theories is so complex that even our most brilliant minds cannot solve it with pen and paper alone. Supercomputers around the world run massive simulations, calculating the properties of thousands of possible calabi-yau shapes to see which ones might yield a universe that looks like ours. They create vast libraries of theoretical data against which we can compare our experimental results. This fusion of silicon and theory is indispensable, allowing us to explore landscapes of possibility that would otherwise remain forever hidden in the realm of the incalculable. This interdisciplinary dance between the abstract and the applied, the infinitesimal and the cosmic, human intuition and machine calculation, is the true engine of modern discovery. It mirrors the history of every great scientific revolution, from the convergence of astronomy and physics that gave us Newton's laws to the blend of chemistry and quantum mechanics that unlocked the secrets of the atom. By breaking down the walls between specialties, researchers can tackle problems that are simply too vast for any one perspective to solve alone, creating a whole that is far greater than the sum of its parts. The search for hidden dimensions, in its very nature, demonstrates that the universe does not respect our artificial academic categories, and to understand its deepest secrets, we must be willing to collaborate as broadly and creatively as the cosmos itself is constructed. Yet as we stand on this thrilling precipice of discovery, it's vital that we pause to consider the profound responsibilities that accompany such a monumental quest. The search for hidden dimensions is not merely a technical or intellectual challenge. It is a deeply human endeavor that inevitably intersects with our values, our beliefs, and our shared future, raising ethical questions we must navigate with care and foresight. One of the most immediate considerations lies in the potential impact on deeply held religious and cultural worldviews. For millennia, human cultures have built rich cosmologies and spiritual understandings based on a three-dimensional world with a linear flow of time. The confirmed existence of additional spatial dimensions, or the revelation that our universe is but one membrane in a vast multiverse, could fundamentally challenge these foundational narratives. This wouldn't necessarily invalidate faith or tradition. Many find the increasing complexity of the cosmos only deepens their sense of wonder and reverence, but it would require a sensitive and thoughtful dialogue between scientific and spiritual communities to integrate this new understanding in a way that respects human dignity and cultural diversity. This leads directly to a perennial question often asked of fundamental research. In a world facing urgent practical problems like climate change, poverty, and disease, can we justify allocating substantial resources to explore what might seem like abstract theoretical concepts? The Large Hadron Collider cost billions of dollars to build and operate. Are such expenditures defensible? History provides a powerful answer, demonstrating that the pursuit of pure knowledge, driven by curiosity rather than immediate application, consistently yields unforeseen and transformative benefits. The development of the World Wide Web at CERN is a classic example, created to help physicists share data and now underpinning global communication. The technologies required for particle accelerators, from advanced superconductors and magnets to unprecedented data processing systems, routinely push the boundaries of engineering and computing, creating spin-offs that benefit medicine, industry, and information technology. Investing in this fundamental research is not a diversion from solving earthly problems. It is an investment in the foundational knowledge and tools that will empower us to solve them in ways we cannot yet even imagine. Furthermore, should we successfully prove the existence of extra dimensions, the potential technological ramifications are staggering and come with their own ethical imperative. The ability to manipulate gravity or access energy from other dimensions could unlock solutions to our energy and environmental crises. However, this same knowledge could also have dual-use potential, applicable in devastating new forms of weaponry or surveillance. This is not science fiction. It is a standard ethical challenge of powerful new technologies, from nuclear fission to genetic engineering. It underscores the critical need for proactive oversight and international cooperation. The scientific community cannot operate in an ethical vacuum. It must work hand in hand with philosophers, policymakers, and the public to establish robust frameworks for responsible research and development long before these technologies become feasible, ensuring they are guided by a commitment to peace, security, and the benefit of all humanity. This necessity for cooperation highlights the inherently global nature of the endeavor. Massive projects like the LHC or the planned LIS Observatory are not owned by any single nation but are collaborative triumphs of international partnership. This model must extend to the governance of the knowledge they produce. The discovery of hidden dimensions would be a milestone for our entire species, and its fruits should be shared as a common heritage. This requires building international treaties and ethical guidelines that promote open collaboration, equitable access to technological advancements, and a shared commitment to preventing misuse. By approaching this quest as a unified human family, we can avoid the pitfalls of a new dimensional arms race and instead foster a future where this profound understanding serves as a bridge between cultures, not a wedge. Ultimately, this is why the conversation must expand beyond laboratory walls. Ethicists and philosophers are increasingly engaging with physicists to anticipate the societal implications of these discoveries, ensuring the relentless pursuit of knowledge remains firmly aligned with human values and well-being. This multidisciplinary dialogue is not a hindrance to scientific progress. It is its essential partner, providing the moral compass to guide us through uncharted territories. The journey beyond the observable is as much about understanding ourselves and our place in the cosmos as it is about unraveling the fabric of space-time. It reminds us that every equation we write and every experiment we conduct is ultimately a human act, embedded in a societal context that demands wisdom, humility, and a profound sense of responsibility for the world we are striving to comprehend and shape. Long before particle colliders or complex equations, humanity was already gazing into the void and sensing a deeper reality. This intuitive pull toward the unseen is a thread woven through the tapestry of countless cultures and traditions across history, each offering its own unique window into a multidimensional cosmos. Consider the profound concept of the dream time in Australian Aboriginal cultures. This is not a distant past but a continuous, parallel dimension of existence, a sacred realm that intersects with our physical world through landscapes, rituals, and stories. It is a foundational reality where ancestral beings shaped the world, and it remains accessible, a dimension of profound spiritual significance that exists alongside our own. Similarly, the rich tapestry of Hindu cosmology presents a universe of astonishing complexity, composed of multiple layers or lokas. These are not merely different planets but distinct planes of existence, realms of divine beings, enlightened sages, and even netherworlds, all coexisting and interpenetrating within the same space, yet vibrating at different frequencies of consciousness. These ancient systems were not developed as scientific hypotheses. They served as spiritual and philosophical frameworks to explain the mysteries of life, death, and our place in a vast, often incomprehensible universe. They provided a language for the sacred, a map for the soul's journey, and an explanation for the forces that shape human destiny, offering a sense of order and meaning that resonates with the same fundamental curiosity driving modern theoretical physics. This human inclination to map the unseen is also deeply embedded in Western thought. The ancient Greek philosopher Plato, with his allegory of the cave, presented a powerful argument that our perceived reality is but a shadow, a dim projection of a more perfect and true realm of ideal forms that exists in a higher state of being. Centuries later, mystical Jewish traditions like the Kabbalah developed intricate maps of the cosmos centered on the Tree of Life, a structure of 10 Sephiroth. These are not physical locations but emanations or dimensions of divine energy through which the infinite, unknowable God interacts with the finite world. Ascending through these spheres was a spiritual pursuit, a journey through layered dimensions of reality toward enlightenment. These historical ideas, while metaphysical, demonstrate a persistent intellectual and spiritual drive to conceptualize a reality that extends beyond our immediate sensory input. Historians of science note that these philosophical and mystical currents often flowed into the streams of early scientific thought, providing a fertile ground of ideas about cosmic order, hidden forces, and the nature of reality that would later be refined by the rigorous methods of empirical inquiry. The alchemists, for instance, sought to transform matter while also seeking spiritual transformation, operating in a world where the physical and metaphysical dimensions were intimately connected. Placing these cultural narratives alongside modern scientific theories reveals a fascinating, though not direct, parallel. It shows a shared human compulsion to explain the world by proposing that what we see is only a fraction of what is there. A string theorist's calabi-yau manifold and a Kabbalist's tree of life are both attempts to describe a hidden, multi-layered architecture underlying the visible universe. They are products of their time, using the tools and languages available to them, mythology, spirituality, philosophy, and mathematics, to answer the same eternal questions. The critical difference, of course, lies in methodology. Science demands testable predictions, falsifiability, and empirical evidence, building a consensus through observation and experiment. Cultural and spiritual beliefs operate in the realms of faith, tradition, and personal experience, offering meaning and moral guidance rather than physical proof. One is not a validation of the other, but recognizing this distinction allows us to appreciate both for what they are: complementary expressions of the human spirit's yearning to transcend the limits of the mundane. This rich cultural context profoundly enriches our appreciation for the modern scientific quest. It reveals that the drive to discover hidden dimensions is not a sudden, isolated phenomenon of the 20th century, but the latest chapter in a continuous human story. We have always used the best tools at our disposal, whether storytelling, ritual, or mathematics, to push against the boundaries of perception and explore the ultimate nature of existence. The physicist working with a supercomputer and the shaman recounting an ancient dreamtime story are, in a deep sense, engaged in a similar endeavor: the attempt to map the unmapped and give voice to the unseen dimensions that shape our reality. This long-standing fascination underscores that the questions we ask today are deeply human questions, connecting our most advanced science to the oldest wisdom traditions in a shared, awe-filled journey to understand the true complexity of the cosmos we inhabit. Looking ahead, the search for hidden dimensions is accelerating, propelled by a new generation of tools that will push the boundaries of observation and theory to places we can barely imagine. In the coming decades, our cosmic perspective will be fundamentally reshaped by instruments like the James Webb Space Telescope, which is already peering deeper into the early universe than ever before. By analyzing the faint light from the first galaxies and the subtle patterns in the cosmic microwave background, astronomers are hunting for anomalies, tiny statistical quirks, or unexpected polarizations that could be the fossilized imprint of multidimensional physics operating in the universe's first moments. A slight deviation from the predictions of standard inflation, for example, could suggest that the rapid expansion of the cosmos was driven not by a simple field in our dimension, but by a dramatic event in the higher dimensional bulk, like a collision between branes. This turns the entire sky into a historical archive, with every photon a potential messenger from a time when the hidden architecture of reality was being forged. On the opposite end of the scale, the future of particle physics hinges on our ability to reach unprecedented energies. While the Large Hadron Collider has explored the tera-electron-volt scale, the next generation of colliders, like the envisioned future circular collider with a circumference of over 50 miles, aims to smash particles at energies an order of magnitude higher. This isn't just an incremental upgrade. It's a leap into a realm where the production of microscopic black holes or the clear signature of a graviton disappearing into an extra dimension could move from a remote possibility to a detectable event. These machines will be complemented by a new class of tabletop experiments that use quantum sensors and superconducting technology to measure the force of gravity at microscopic distances with insane precision. If gravity begins to deviate from Newton's inverse square law at a scale of mere microns, it would be a stunning direct indication that the force is spreading out into a large, hidden dimension, finally solving the hierarchy problem not with abstract math, but with hard, empirical data. Theoretical research is also poised for a revolution, driven by an increasingly powerful partnership with artificial intelligence and advanced computing. The mathematics of string theory and its landscape of possible universes is so complex that mapping it requires a synergy between human intuition and machine learning. AI algorithms are now being trained to explore the vast library of possible calabi-yau manifolds, searching for the specific geometric shapes that yield the precise particles and forces we observe in our universe. This could dramatically narrow down the countless possibilities to a handful of viable candidates, transforming string theory from a broad framework into a predictive engine that makes specific, testable forecasts for future experiments. Furthermore, the emerging field of quantum computing offers the tantalizing prospect of simulating quantum gravity effects in ways classical computers never could, allowing us to virtually experiment with the fabric of spacetime itself and observe how dimensions might emerge from the quantum foam. This monumental effort is inherently interdisciplinary, forging connections between fields that were once considered separate. Cosmologists, particle physicists, mathematicians, and computer scientists are now in constant dialogue, recognizing that the clues to the universe's deepest secrets are scattered across all domains of knowledge. The data from a gravitational wave observatory like LISA might be cross-referenced with the results from a particle collider, while a theoretical insight from a mathematician working on knot theory could provide the key to interpreting an anomaly in the cosmic microwave background. This collaborative spirit is the new paradigm for discovery, breaking down the silos between specialties to tackle problems that are simply too vast for any one discipline to solve alone. Underpinning all of this technical progress is the essential role of public engagement and education. The quest to understand the fundamental nature of reality is a profoundly human one, and maintaining public support for these big, curiosity-driven projects requires clear and inspiring communication. Through documentaries, planetarium shows, and interactive online content, scientists and educators are working to translate these complex ideas into stories that resonate with a broad audience, fostering a sense of shared wonder and investment in the journey. This ensures that the search for hidden dimensions remains a collective human adventure, not just an academic pursuit, and inspires the next generation of diverse thinkers who will carry the torch forward. The potential payoff for all this effort is nothing less than a complete rewriting of the textbooks. Confirming the existence of hidden dimensions would be a pivotal moment in human history, on par with the Copernican revolution or the discovery of quantum mechanics. It would provide the missing piece for a unified theory of everything, elegantly weaving together gravity and the quantum world into a single, coherent tapestry. But the implications would ripple far beyond theoretical physics, transforming our understanding of everything from the birth of the cosmos to the nature of consciousness itself. It would prove that reality is far grander, more complex, and more interconnected than we ever dared to dream, a magnificent multidimensional landscape waiting to be explored. The journey ahead is filled with challenges, but each one is an invitation to learn, to innovate, and to push further into the magnificent unknown. Ultimately, this grand scientific pursuit resonates on a deeply personal level because it taps into something fundamental within us all, that innate, childlike sense of wonder when we first look up at a star-filled sky. The search for hidden dimensions is a modern expression of that ancient, universal curiosity, a formalized and rigorous way of asking the very same questions that have captivated philosophers, poets, and dreamers for millennia. Why are we here? What is this place made of, and is there more to existence than what meets the eye? This quest validates that deep-seated feeling many of us have had, that intuition that the world is more mysterious and magnificent than it appears on the surface. It tells us that our wonder is not misplaced, but is in fact a crucial compass pointing toward profound and unexplored truths about the universe we call home. Engaging with these ideas also cultivates a powerful and essential intellectual humility. In our daily lives, it is easy to operate under the assumption that we have a firm grasp on reality, that the world is essentially as we perceive it. The possibility of hidden dimensions shatters that comfortable certainty, offering a stunning reminder that our perception is incredibly limited, filtered through a narrow biological lens evolved for survival on a particular planet, not for perceiving the full, rich tapestry of the cosmos. This realization is not meant to make us feel small or insignificant, but to inspire a beautiful sense of awe and a recognition of how much there is left to learn. It encourages a mindset of open-mindedness, where we are always prepared for the next discovery to completely overturn our assumptions, teaching us to embrace the unknown not with fear, but with excited anticipation. This journey also showcases the very best of what humanity can achieve when we work together. The search for extra dimensions is not the project of a lone genius in an isolated lab. It is a monumental, global collaboration. It connects theoretical physicists in California with engineers in Switzerland, data analysts in Japan, and telescope operators in Chile. It requires the shared expertise of mathematicians, computer scientists, and astronomers from every corner of the world, all contributing their unique skills to a common, awe-inspiring goal. In an era often defined by division and conflict, this shared scientific endeavor stands as a powerful testament to our common humanity and our collective potential. It proves that our deepest questions can transcend borders and backgrounds, uniting us in a shared mission to unravel the mysteries of existence, reminding us that we are all explorers on the same tiny, fragile planet, gazing out at the same vast, mysterious universe. On an individual level, delving into these concepts provides a unique form of intellectual and spiritual nourishment. In a world often consumed by the immediate and the mundane, the daily news cycle, the demands of work, the endless stream of digital distractions, these ideas offer a refreshing and expansive perspective. They invite us to lift our gaze from our screens and contemplate the fundamental architecture of reality itself. This engagement is not a passive act of receiving information. It is an active exercise for the mind, a form of mental stretching that is both challenging and deeply rewarding. It allows us to participate, even as amateurs, in the greatest detective story of all time, piecing together clues from the largest scales of the cosmos and the smallest scales of quantum foam to guess at the blueprint of everything. This process is inherently enriching, connecting us to a larger story of discovery and filling us with a sense of profound awe that can feel, for many, like a spiritual experience. The relentless pursuit of these hidden truths embodies the most admirable human qualities: creativity to envision realities beyond our senses, perseverance to continue the search across generations despite countless setbacks, and an unwavering commitment to truth wherever it may lead. This is not a dry, academic exercise. It is a vibrant, dynamic, and deeply human adventure. It demonstrates that science, at its heart, is not a cold collection of facts but a living, breathing process of inquiry driven by passion, imagination, and a boundless curiosity about our place in the grand scheme of things. This personal connection transforms the quest from an abstract scientific problem into a deeply relatable human story, reminding each of us that the drive to look beyond the horizon, to ask what lies just out of view, is an essential part of who we are. It invites every single one of us to be curious, to wonder, and to never stop marveling at the incredible, hidden depths of the universe we inhabit. Perhaps no single machine embodies humanity's ambition to peek behind the curtain of reality more than the Large Hadron Collider, a monumental 17-mile ring of supercooled magnets and detectors buried beneath the border of France and Switzerland. This colossal instrument is far more than just the world's most powerful microscope. It is a time machine capable of recreating the searing conditions that existed a fraction of a second after the Big Bang. Within the debris of these microscopic fireballs, physicists meticulously sift for clues, and for years, one of their most tantalizing quarries has been the faint, ghostly signature of extra dimensions. The primary strategy in this hunt is deceptively simple. Look for energy that seems to vanish into thin air. We know from the unbreakable law of conservation of energy that energy cannot be created or destroyed, only transformed. In the incredibly precise environment of a particle collision, scientists can account for the energy going in and measure the energy of all the particles coming out. But if extra dimensions exist, there's a potential escape route. A particle, particularly the hypothetical carrier of gravity known as the graviton, could be kicked with such immense force that it doesn't just travel through our familiar dimensions, but briefly moves into a compactified or bulk dimension. From our three-dimensional perspective, the energy carried by that particle would simply disappear, leaving behind an event that seems to defy a fundamental law of physics. Finding a statistically significant number of these missing energy events would be a powerful, indirect whisper from a hidden realm. Beyond missing energy, the LHC has been searching for even more spectacular phenomena. Some Brane world models suggest that if extra dimensions are large enough, the colossal energies of these proton collisions could actually warp space-time enough to create microscopic black holes. Now, before visions of a cosmic vacuum cleaner emerge, these would be unimaginably tiny and ephemeral objects. Governed by the laws of quantum mechanics, they would instantly evaporate in a burst of radiation, known as Hawking radiation, in a fraction of a nanosecond. This evaporation would leave behind a very specific and explosive spray of particles in the detectors, a clear and unmistakable fingerprint of their brief existence. While the LHC has not yet observed this spectacular signature, its searches have been crucial. By not finding these black holes, the experiments have effectively ruled out entire families of theories that predicted they should be easily produced at these energy scales, forcing theorists to refine their models and consider new possibilities for how these dimensions might be configured. Another key search has been for particles known as Kaluza-Klein states, a direct nod to the pioneers of the field. These would be like heavier, excited vibrational twins of the standard particles we know. If an electron, for instance, could move through an extra compactified dimension, it wouldn't just have one mass. It could have a whole spectrum of masses corresponding to the different ways it can vibrate through that hidden direction. Finding a particle that behaves exactly like an electron but with a much higher mass would be a direct echo from a higher dimensional reality. The LHC's powerful detectors, like a TLS and CMS, have been meticulously scanning their data for any sign of these heavy partners, but so far they have not appeared. This absence, however, is far from a failure. Each null result acts like a cartographer shading out uncharted territories on a map, telling us where these dimensional phenomena cannot be. The experiments have placed stringent lower limits on the possible masses of these Kaluza-Klein particles and gravitons, effectively telling theorists that if these dimensions exist, they must be either smaller or configured in a more complex way than previously thought. The phenomenal success of the LHC in discovering the long-sought Higgs boson in 2012 actually plays a critical role in this dimensional search. The discovery confirmed that the standard model of particle physics, while incomplete, is an incredibly robust and accurate description of reality up to the energies we have probed. This success gives physicists immense confidence in the machine itself and in their ability to understand its complex data. It proves that if a predicted particle within the energy range of the collider exists, the LHC has the power to find it. This confidence is essential when looking for the subtle and rare signals that could point to extra dimensions. It means that when the detectors do see an anomaly, researchers can be more certain that it might be new physics and not just an unexplained fluctuation or a misunderstanding of the known physics in the extreme environment of a collision. This entire process beautifully illustrates the iterative, often painstakingly slow nature of scientific discovery. The quest for hidden dimensions is not a straightforward path to a eureka, a moment, but a meticulous process of elimination and refinement. Each time the LHC completes a run and its analysts pore over the petabytes of data, they are not just looking for a discovery, they are also building higher and higher fences around the island of known physics, constraining the wilder possibilities of theory with the unyielding concrete of experimental data. This is how science truly progresses, not only by what we find, but by what we rule out. The fact that we have not yet found definitive evidence for extra dimensions at the LHC is, in itself, a profoundly valuable result, guiding theorists away from dead ends and toward more sophisticated and nuanced models of higher dimensional space. The hunt is far from over. With ongoing upgrades to increase the collider's luminosity and energy, and with ambitious plans for a future collider potentially 3 times larger, the search will continue with ever greater precision, ensuring that this grand experimental effort remains one of humanity's most dedicated attempts to answer a timeless question: is there more to reality than what we can see? Beyond the complex equations and the relentless pursuit of empirical proof, there exists another, more visceral reason why the idea of hidden dimensions has captured our collective imagination for over a century: its sheer, breathtaking beauty. This isn't just a scientific quest, it's an aesthetic one. The same mathematical elegance that makes theories like string theory so compelling to physicists also resonates with a deep human appreciation for harmony, pattern, and sublime form. Consider the calabi-yau manifold, the intricate 6-dimensional shape thought to define the universe's hidden geometry. To a mathematician, its value lies in its specific properties, but to an artist, it's a form of stunning complexity and symmetry, a multi-faceted jewel with a structure so perfect it seems almost too beautiful not to exist in nature. These shapes, visualized through powerful computer modeling, become digital sculptures, twisting and turning in ways that defy our 3-dimensional intuition, yet possess a visual logic and balance that feels intrinsically right. They are the blueprints of reality, and they look like works of art. This aesthetic appeal has sparked a fascinating dialogue between science and the broader culture, inspiring a wave of creativity that helps translate these abstruse concepts into something tangible and emotionally resonant. Artists, filmmakers, and designers frequently draw from the well of theoretical physics, creating visuals that strive to evoke the wonder of multidimensional spaces. The iconic tesseract from the film Interstellar is a perfect example, a hypercube unfolding in 4 spatial dimensions, represented as a mesmerizing, complex structure of light and connecting lines. It wasn't a literal scientific diagram, but an artistic interpretation that captured the feeling of a higher dimensional object, making the abstract momentarily tangible and filling audiences with a sense of awe. Similarly, science museums around the world use immersive projections and interactive installations to create experiential models of curled-up dimensions, allowing visitors to feel, in a small way, what it might be like to perceive a reality beyond our own. This artistic bridge is crucial because it makes the science accessible, not by dumbing it down, but by appealing to our innate sense of wonder. It allows someone with no background in differential geometry to stand before a visualization of a calabi-yau manifold and simply feel that they are in the presence of something profound and beautiful. This intersection speaks to a fundamental human desire to find coherence and order in the cosmos. The symmetries and harmonies embedded in the mathematics of hidden dimensions fulfill a deep-seated need for a universe that is not just random and chaotic, but structured and elegant. There is a profound comfort and intellectual satisfaction in the idea that the bewildering zoo of subatomic particles and the fundamental forces that bind them could all emerge from the vibrational notes of a single type of string, dictated by the geometry of a hidden dimension. It suggests a universe built on a foundation of musical harmony, a cosmic symphony where every particle is a note and every law of physics is a chord. This perspective transforms physics from a mere catalogue of facts into a search for a grand, unifying beauty, a theory that is not only true but also inevitably, powerfully elegant. By embracing both the rational and the beautiful, we enrich our understanding of these ideas immeasurably. The aesthetic dimension invites a different mode of engagement, one that is intuitive and emotional rather than purely analytical. It allows us to appreciate the majesty of theoretical physics on a human level, connecting it to our love of art, music, and nature. This fusion reminds us that the pursuit of knowledge is not a cold, clinical exercise but a deeply human endeavor, driven by the same cravings for meaning, pattern, and splendor that inspire our greatest artistic achievements. As we marvel at the elegant dance of equations that describe a 10-dimensional universe or lose ourselves in an artist's rendering of a higher dimensional space, we are participating in a timeless tradition. The celebration of the beautiful mystery at the heart of existence, where truth and beauty are not separate paths, but 2 sides of the same magnificent coin. Imagine for a moment that the universe operates under 2 completely different sets of rules. On the grand scale of galaxies and the fabric of spacetime itself, Einstein's general relativity reigns supreme, describing gravity as the elegant curvature of a 4-dimensional continuum. It's a geometric masterpiece, but zoom into the quantum realm, to the world of atoms and subatomic particles, and a different, bizarre set of laws takes over, a probabilistic, fuzzy world governed by quantum mechanics. For nearly a century, these 2 pillars of modern physics have stood in brilliant, yet utterly incompatible, isolation. General relativity cannot explain the random, quantized behavior of the tiny, and quantum mechanics completely fails to describe the smooth, geometric force of gravity. This fundamental rift is more than just an academic inconvenience. It's a glaring crack in the foundation of our understanding, a sign that a deeper, more complete truth is waiting to be discovered. This is where the quest for hidden dimensions transforms from a fascinating theoretical exercise into an essential journey toward unification. The ultimate dream of physics is a single, all-encompassing framework often called the theory of everything, a set of equations so powerful and elegant that they can describe every force, every particle, and every interaction in the cosmos, from the frantic dance of quarks to the majestic swirl of galaxies under one unified roof. Hidden dimensions are not just a quirky add-on to this idea. They are potentially the very key that unlocks the door. Think of it like this. If gravity appears impossibly weak compared to the other forces, perhaps it's because its true strength is being shared across dimensions we cannot perceive. By inviting gravity to play in a higher dimensional arena, we can finally bring it to the same table as electromagnetism and the nuclear forces, allowing them to be described by a common, geometric language. String theory and its more advanced successor, M-theory, are the most developed frameworks offering this profound vision. Their core premise is one of breathtaking simplicity. If every fundamental particle is actually a different vibrational mode of a tiny, one-dimensional string, then the forces between them aren't handed down by arbitrary rules but emerge naturally from how these strings interact and oscillate. However, for this beautiful mathematical symphony to work, the strings need room to vibrate. The equations themselves demand extra spatial dimensions, 6 or 7 of them, curled up into an intricate shape at every point in space. In this view, the reason for the apparent conflict between gravity and the quantum world isn't a fundamental incompatibility, it's a perspective problem. We are like flatlanders trying to understand a sphere, only seeing a sliver of the full, multidimensional picture. Unification becomes a geometric inevitability once we acknowledge the complete, hidden architecture of reality. The power of a truly unified theory would be revolutionary. It would do for physics what James Clerk Maxwell's equations did in the 19th century when they unified electricity, magnetism, and light into a single, elegant framework of electromagnetism. Before Maxwell, these were seen as separate phenomena. Afterward, they were understood as different manifestations of a single underlying force. A theory of everything based on hidden dimensions would represent a leap of that same magnitude, but for all of reality. It wouldn't just patch over the differences between quantum mechanics and general relativity. It would reveal them both as different facets of a much deeper, simpler, and more beautiful principle. The bewildering complexity of the standard model of particle physics, with its zoo of seemingly arbitrary particles and forces, could be seen as the inevitable outcome of the vibrational patterns of strings within a specific calabi-yau manifold. The laws of nature would no longer seem like a list of unrelated constants, but as the unique mathematical output of the universe's hidden geometry. This quest for unification is driven by a deep-seated belief that the universe is fundamentally simple, elegant, and coherent at its core. Physicists are guided by the conviction that nature does not employ a separate rulebook for every scale and every phenomenon. The relentless drive to find this underlying harmony is what fuels researchers to tackle problems that may not be solved in their lifetimes. It's a journey that requires immense creativity, mathematical rigor, and a steadfast faith that the pieces will eventually fit together. Every null result from a particle collider, every refined gravitational wave measurement, and every new insight into the mathematics of higher dimensional spaces is a step toward reconciling the very large with the very small, inching us closer to a coherent description of reality that is as powerful as it is beautiful. This vision of a unified cosmos where all forces are woven together through the fabric of hidden dimensions remains one of the most inspiring and ambitious goals in all of human thought. Now, as thrilling as these ideas are, it's crucial to separate the rigorous science from the rampant speculation that often surrounds it. One of the most common misconceptions is that extra dimensions are purely the stuff of science fiction, a fantastical concept with no grounding in real physics. While it's true that science fiction loves to play with these ideas, the theories we've been discussing, from Kaluza-Klein to string theory and Brane worlds, are built on a foundation of complex, sophisticated mathematics. They aren't wild guesses, they are detailed models developed to solve specific, thorny problems in our understanding of the universe, like unifying gravity with quantum mechanics or explaining the shocking weakness of the gravitational force. The leap from fiction to science happened nearly a century ago, and it's been a serious, peer-reviewed field of study ever since. Another popular but mistaken belief is that these dimensions would be like the alternate realities or parallel universes, often depicted in movies and comics, where you could hop over to a dimension where dinosaurs never went extinct or you became a rock star. In physics, extra dimensions aren't other worlds with their own independent histories. They are additional directions in space, woven into the very fabric of our own universe. If they exist, they follow specific, lawful physical principles and interact with our familiar dimensions in predictable, mathematically defined ways. A curled-up dimension doesn't host an alternate version of you. It influences the mass of an electron or the way gravity behaves at tiny scales. The interaction is subtle, geometric, and governed by equations, not a gateway to endless fantasy scenarios. This leads to a related myth about time travel. Many people hear fourth dimension and immediately think of H.G. Wells' time machine, where a fourth spatial dimension allows for travel through time. In physics, time is already considered a dimension in our four-dimensional spacetime continuum. The proposed extra dimensions are additional spatial dimensions, not temporal ones. There's no serious scientific theory that suggests moving through a higher spatial dimension would allow you to travel back to the past. These dimensions are about the structure of space itself, not a bypass for causality. There's also a widespread expectation that the discovery of extra dimensions would instantly lead to dramatic technological revolutions, warp drives, gravity manipulation, or portals to other worlds. While uncovering the fundamental architecture of reality could have profound long-term implications, any practical applications would be incredibly distant and almost certainly indirect. The immediate impact would be a monumental revolution in our understanding, not our technology. The real payoff would be intellectual, finally grasping how the universe works at its most fundamental level. Any future technology would stem from that deep knowledge, but it would require centuries of engineering development that we can scarcely imagine today. Much like understanding quantum mechanics didn't immediately give us smartphones but paved the way for them decades later. Ultimately, dispelling these myths isn't about crushing wonder, it's about channeling it in the right direction. The true story of hidden dimensions is in many ways more fascinating than the fiction. It's a story of human curiosity using the powerful tools of mathematics and experimentation to probe the deepest layers of reality, guided by evidence and rigorous thought. By clearly communicating the real science, educators and scientists can foster a more accurate public discourse, one that appreciates the genuine mystery and potential of this quest without the distraction of misleading tropes. This builds a solid foundation for informed engagement, ensuring that as this incredible search continues, the excitement is fueled by the awe of real discovery, not just the allure of science fantasy. But to truly grasp how such an abstract concept could dictate the laws of our physical world, we need to explore one of the most powerful and beautiful ideas in all of science: symmetry. This isn't just about something looking the same on both sides. In physics, symmetry is a profound principle that a law of nature remains unchanged under a specific transformation. Think of a perfect sphere. You can rotate it any way you like and it looks identical. That rotational symmetry is a property of its shape. Now, imagine that same principle applied not to objects, but to the very fabric of the universe itself. This is where our journey into hidden dimensions takes a deeply mathematical turn, guided by the elegant language of group theory and gauge theories. These are the formal frameworks that allow physicists to classify the possible types of symmetries a system can have. When we propose that our universe has extra, compactified dimensions, we are essentially proposing that space-time possesses a new, hidden symmetry. The specific way these dimensions are folded and curled, their geometry, defines a set of symmetries, and it is these symmetries that ultimately dictate everything we observe. They act as a kind of cosmic filter, determining which vibrational patterns of strings are allowed and which are forbidden, which in turn fixes the masses of particles and the strengths of the fundamental forces. In this breathtaking view, an electron has its specific mass not by random chance, but because the hidden six-dimensional shape of the universe possesses a specific symmetry that resonates at that particular frequency. This profound link between geometry and physics becomes spectacularly clear when we examine a concept like supersymmetry. This is a hypothetical symmetry that goes beyond our familiar three dimensions of space, proposing a deep relationship between the two fundamental classes of particles: fermions, which are the building blocks of matter like quarks and electrons, and bosons, which are the force carriers like photons and gluons. Supersymmetry suggests that for every known particle, there should be a superpartner with a different quantum spin. This isn't just a whimsical idea. It's a symmetry that many theorists believe is necessary to make the math of string theory work consistently in a 10-dimensional universe. But its potential benefits ripple directly into our 4-dimensional reality. One of the most pressing issues it could solve is the infamous hierarchy problem, the puzzling, enormous gap in strength between gravity and the other forces. In the Standard Model, the mass of the Higgs boson is incredibly sensitive to quantum corrections, requiring an absurdly precise and unnatural fine-tuning to keep it from skyrocketing to the Planck scale. Supersymmetry elegantly cancels out these problematic corrections, stabilizing the Higgs mass and offering a natural explanation for why the scales of particle physics and gravity are so different. It demonstrates how a symmetry rooted in the requirements of higher dimensional physics can provide a graceful solution to a stubborn problem in our observable world, weaving together the quantum realm with the geometric framework of hidden dimensions. The quest to map these unseen realms is therefore a quest to find the universe's lost chord, the specific symmetrical shape whose resonant frequencies produce the exact symphony of particles we observe. Theorists don't just guess at these shapes, they use the stringent requirements of mathematical consistency as their guide. They might start with a simple, symmetrical shape like a circle or a torus, a donut shape, but the need to incorporate fermions and the chiral structure of the Standard Model, meaning the fact that nature makes a distinction between left-handed and right-handed particles, forces them toward more complex geometries. This is where objects like calabi-yau manifolds enter the stage. These are not arbitrary complicated shapes. They are the ones that possess the very specific types of symmetries required by superstring theory. Their intricate, multi-hold structures are a visual representation of a complex symphony of symmetries, and each different calabi-yau manifold represents a different possible universe with a different set of physical laws. The challenge for physicists is to work backwards, using the known constants of our universe as a fingerprint to identify which of these countless symmetrical shapes might be the true ground state of our reality. This process is a testament to a deep-seated belief that drives fundamental research, that the universe is not arbitrary or chaotic, but inherently orderly and comprehensible. The emphasis on symmetry reflects a faith that beneath the apparent complexity of the natural world lies a foundation of elegant mathematical beauty. By studying these symmetrical structures, we are not just doing abstract math. We are gathering the tools to decode the hidden architectural plans of existence itself, demonstrating that the most profound truths about the concrete physical world are often written in the abstract language of geometry and symmetry. To truly appreciate the unique place that hidden dimensions hold in modern science, it helps to compare this quest to our pursuit of other great cosmic mysteries. Consider dark energy, the enigmatic force accelerating the expansion of the universe. We can directly observe its profound effects on the largest scales of the cosmos, watching galaxies recede from us at ever-increasing speeds, yet its fundamental nature remains utterly unknown. It is an observable effect in desperate need of a cause. The nature of time presents another fascinating puzzle, why it seems to flow in one direction, creating a stark asymmetry in a universe whose laws are largely time-symmetric. These are mysteries born from direct observation, phenomena we can measure but cannot yet explain within our existing frameworks. The search for hidden dimensions operates from a slightly different, yet equally vital scientific impulse. Rather than explaining a direct observation, extra dimensions are a theoretical proposal invoked to solve deep-seated inconsistencies within our current best theories. They are a potential answer to a why question. Why is gravity so unimaginably weaker than the other fundamental forces? Why do the laws of quantum mechanics and general relativity refuse to speak the same language? In this sense, the pursuit is less about explaining a new observation and more about completing an incomplete picture, much like a detective proposing the existence of an unseen suspect to make sense of all the clues at a crime scene. This is a time-honored tradition in physics. The neutrino, for instance, was first proposed by Wolfgang Pauli in 1930 as a desperate remedy to explain the apparent missing energy in certain radioactive decays, a particle so elusive it wasn't directly detected for another 26 years. Similarly, the Higgs boson was a theoretical prediction for decades before the Large Hadron Collider confirmed its existence, its field necessary to explain why other particles have mass. Hidden dimensions fit squarely into this lineage. Bold theoretical constructs propose to restore harmony and consistency to our mathematical description of reality. What makes the current era so thrilling is the remarkable synergy developing between these different frontiers of ignorance. The quest to understand hidden dimensions is no longer an isolated theoretical exercise. It actively fertilizes and is fertilized by progress in other fields. In cosmology, the precise measurements of the cosmic microwave background by missions like Planck provide a data set against which physicists can test models of the early universe that incorporate higher dimensional physics, such as certain inflationary scenarios driven by brane collisions. Conversely, the mathematics developed for string theory and extra dimensions, particularly in areas like quantum field theory and holography, has provided cosmologists with powerful new tools to model the complex evolution of the universe. In the realm of quantum information science, the mind-bending phenomenon of entanglement is now being studied through the lens of geometry, with some physicists proposing that the strange, instantaneous connection between particles might be facilitated by shortcuts through extra dimensions. This cross-pollination of ideas is accelerating discovery, demonstrating that a breakthrough in one area could very well provide the key to unlocking another. This holistic view reveals a beautiful truth about the scientific endeavor. Our attempts to understand the cosmos are all deeply interconnected. The scientist studying the gravitational waves from colliding black holes and the researcher probing the quantum entanglement of particles in a lab are, in a profound way, working on different facets of the same grand puzzle. They are all charting the same unknown territory, just using different maps and instruments. By viewing these mysteries in tandem, dark energy, quantum gravity, the nature of time, and hidden dimensions, we gain a richer appreciation for the complexity of the universe and the creativity of the human mind striving to comprehend it. This perspective fosters a collaborative spirit that breaks down the traditional barriers between scientific specialties, encouraging a free flow of ideas that is essential for the kind of paradigm-shifting discoveries we all hope for. The search for dimensions beyond our perception is therefore more than a niche interest. It is a vital part of a much broader, collective effort to weave all of physical reality into a single, coherent, and breathtaking tapestry. This grand and ongoing quest, this collective human effort to glimpse beyond the veil of our four-dimensional reality, has been propelled forward by a remarkable cast of visionary thinkers. They are the pioneers who dared to imagine the unimaginable, the mathematicians who provided the language for that imagination, and the experimentalists who devised ways to ask the universe for answers. At the very dawn of this idea stand two figures whose work was so far ahead of its time it was nearly forgotten: Theodore Kaluza and Oskar Klein. In 1921, Kaluza performed what can only be described as mathematical magic. By taking Einstein's equations for gravity in four-dimensional spacetime and simply adding one more dimension, he found that the new, expanded set of equations not only still described gravity, but also perfectly produced the equations for Maxwell's theory of electromagnetism. It was a stunning, elegant unification, suggesting that light and gravity were two sides of the same higher dimensional coin. The immediate and obvious question was, of course, where is this fifth dimension? This is where Oskar Klein made his crucial contribution just a few years later. He proposed that this extra dimension wasn't vast and expansive like the others, but was instead curled up into a circle so incredibly tiny, on the scale of the Planck length, that it was completely invisible to any possible measurement. Their Kaluza-Klein theory was a masterpiece of mathematical beauty, but as the wild and wonderful world of quantum mechanics exploded onto the scene, their radical idea was shelved, a brilliant but seemingly incomplete symphony waiting decades for its next movement. That next movement would be led by a new generation of theorists who picked up the torch with renewed vigor and deeper mathematical insight. Among them, figures like Edward Witten stand as giants. A theoretical physicist often described by his peers as the foremost authority on string theory, Witten's contributions have been pivotal in advancing our understanding of how hidden dimensions might actually work. His work on M-theory in the 1990s was a seismic event in the field, proposing that the 5 different versions of string theory were not competitors but merely different perspectives on a single, underlying 11-dimensional theory. This was a monumental step toward a more unified vision, suggesting a cosmos with a richer, more complex dimensional architecture than anyone had previously considered. Witten's profound mathematical prowess helped to solidify the credibility of the entire endeavor, pushing the mathematics of calabi-yau manifolds and higher dimensional spaces to new frontiers, and inspiring countless other physicists to explore this breathtaking landscape of ideas. His career exemplifies the sheer intellectual creativity required to map the uncharted territories of theoretical physics, demonstrating that progress often comes from a deep and intuitive conversation with the mathematics itself. Yet a beautiful theory, no matter how elegant, remains an incomplete picture until it is confronted with experimental evidence. This is where the courageous work of experimentalists like Fabiola Gianotti becomes absolutely essential. As a brilliant particle physicist and the first woman to serve as Director General of CERN, Gianotti led the ATLAS collaboration, one of the two major teams at the Large Hadron Collider that co-discovered the Higgs boson in 2012. While that discovery confirmed the last missing piece of the Standard Model, the hunt for physics beyond it, including the subtle signs of extra dimensions, continues under her leadership. Orchestrating the work of thousands of scientists, engineers, and technicians, managing one of the most complex machines ever built, and steering the global scientific agenda toward these fundamental questions requires a different kind of genius. It demands impeccable organizational skill, unwavering determination, and a deep commitment to collaborative truth-seeking. Gianotti's work embodies the practical, gritty side of the quest, transforming abstract mathematical speculation into a rigorous, data-driven investigation, and ensuring that our most ambitious theories are always grounded in the unyielding reality of experimental proof. But the story of this search is not confined to academic papers and laboratory walls. It has been captured and conveyed to the public with infectious enthusiasm by master communicators like Michio Kaku. A theoretical physicist himself, Kaku has dedicated much of his career to translating the complex, often bewildering concepts of higher dimensional physics into language that sparks wonder in millions. Through best-selling books like Hyperspace and Parallel Worlds, and countless television and online appearances, he has become a friendly and familiar guide into the world of branes, strings, and multidimensional cosmos. His gift is making the seemingly impenetrable feel accessible and exciting, helping people understand why a 9-dimensional universe might matter and how it could reshape our entire conception of reality. This work of public engagement is not a sideline, it is vital. It cultivates a sense of shared curiosity and wonder, inspires the next generation of scientists, and helps build the broad base of public support that makes enormous, long-term projects like the LHC possible. Kaku and communicators like him ensure that this incredible journey remains a human story, one that belongs to all of us. Together, these individuals and the thousands of collaborators standing with them represent the multifaceted engine of scientific discovery. They remind us that progress is not a solitary endeavor but a vast, collaborative tapestry woven from threads of bold intuition, mathematical rigor, meticulous experimentation, and passionate communication. Their stories are testaments to human curiosity and perseverance, often pursued for decades without any guarantee of success, driven simply by the belief that a deeper truth is waiting to be found. They faced and continue to face technical challenges of staggering complexity and occasional skepticism from within the scientific community, yet they persist. By celebrating these inspirational figures, we do more than just recount history. We honor the very human spirit of exploration that pushes us to look beyond the horizon of the known. Their collective legacy is a beacon, encouraging us all to keep asking the big questions, to embrace the unknown with excitement, and to continue the never-ending, awe-inspiring quest to understand our place in this magnificent, multidimensional universe. Our journey through the fascinating quest for hidden dimensions has revealed a universe far richer and more complex than we ever imagined, where extraspatial realms could hold the keys to unifying physics and explaining cosmic mysteries. We started by peering into the past, watching as visionaries like Kaluza-Klein first dared to add a new direction to reality itself, setting a profound idea into motion. From there, we ventured into the intricate world of string theory, where the very notes of existence are plucked on tiny, vibrating strings, and explored the startling possibility that our entire universe might be a membrane floating within a vast, higher dimensional bulk. We saw how this incredible framework isn't just abstract math. It's a potential answer to some of science's most stubborn puzzles, from the shocking weakness of gravity to the ghostly nature of dark matter. We've followed the hunt for these unseen realms from the colossal experiments at the Large Hadron Collider, searching for energy that vanishes into the void, to exquisitely sensitive tabletop devices feeling for the faintest whisper of gravity's true strength. This pursuit is a perfect symphony of human ingenuity, a blend of bold imagination and relentless rigor, where theoretical elegance meets hard, empirical evidence. It shows us that science at its best is a collaborative, global effort, uniting minds across disciplines and continents in a shared drive to understand the deepest architecture of everything. While the definitive proof remains just beyond our current grasp, the very act of searching expands the horizons of human knowledge and technology in ways we can't yet foresee. The questions we ask today, no matter how abstract, have a way of shaping the world of tomorrow. This quest, in the end, is about more than just dimensions. It's a reflection of our species' insatiable curiosity, our desire to look beyond the apparent limits and discover what else is out there. Thank you for joining this incredible adventure into the unknown. If this journey through the cosmos's hidden layers sparked your wonder, please show your support by liking this video, sharing it with fellow curious minds, and subscribing to our channel for more explorations into the wonders of space and science. We are genuinely eager to hear what you think down in the comments. What aspect of hidden dimensions captured your imagination the most? Was it the elegant beauty of calabi-yau manifolds, the brain-bending concept of brane worlds, or the thrilling possibility of one day detecting a signature in a particle collider? Let's keep the conversation going. Until next time, keep looking up and never, ever stop wondering about the magnificent mysteries that lie just